Step into the shadows of the ocean's deepest reaches, where the outlines of sunken ships and shattered submersibles emerge from darkness. You will witness expeditions that sought lost treasures and hidden vessels, only to encounter the ocean's unrelenting force. Feel the weight of pressure and silence as copper hulls twist, instruments fracture, and cargo disappears into silted depths. As you follow the traces of these ill-fated journeys, every anomaly and fragment tells a story of ambition, miscalculation, and the mysteries the sea refuses to surrender. In these depths, nothing is quite as it seems, and each revelation draws you further into a world both fragile and unforgiving. The descent to Kraken Ridge. The waters surrounding the remote volcanic corridor known as Kraken Ridge had long drawn the attention of oceanographers, yet it was the deep-sea recovery expedition dispatched to retrieve a missing autonomous lander that brought its name back into quiet discussion. At first, the mission seemed routine, a search for a research drone that had transmitted its final signal from just above the ridge's blistered terrain. The operators overseeing the descent treated the assignment as another demanding retrieval, confident in the submersible's reinforced hull and the team's experience operating within a tectonically active zone. As the vessel sank toward the ridgeline, the surrounding water grew hazy from suspended sediments loosening along the slopes. Kraken Ridge, positioned where the mid-Atlantic ridge begins to twist into irregular fractures, had developed a reputation for unusual thermal signatures and unpredictable hydrothermal chimneys, although most research teams considered its anomalies simply the products of dynamic geology. It became clear that the ridge was unusually restless that day, its vents opening and closing with a mechanical steadiness uncommon in natural systems. Still, the deeper the sub went, the more the water felt charged with a low, resonant thrum. In the mid-water column, the team detected the lander's transponder signal pulsing at uneven intervals. What unsettled the operators was the echo beneath each pulse, a faint secondary resonance that seemed to respond rather than reflect. Even in the cleanest readings, sonar rarely behaved in such a conversational rhythm. The expedition continued, tracking the signal into a shadowed channel formed by two towering columns of basalt, rising from the ocean floor like petrified sentinels. Near the base of these structures, the water pressure rose with its typical steadiness, but the instruments registered something new, abrupt micro-fluctuations, as though compressed pockets were continuously forming and collapsing ahead of the sub. The crew compensated, but one scientist monitoring the pressure logs remarked that such fluctuations usually appeared around vent systems under extreme stress. The ridge seemed to tighten around them, its rugged topography closing into narrower passages that filtered what little light the submersible carried. Visibility dropped to a muted blue haze. When the lander finally appeared on sonar as a solid return, the team slowed to a careful crawl. The drone rested in a shallow depression carved into the ridge's flank, its frame intact but covered in a fine layer of black particulate. This dust-like coating suggested volcanic discharge, the kind produced when superheated minerals cool rapidly upon contact with seawater. Its metallic readings were richer, almost uniform, as if the particles had been cast from a single source. The recovery crew prepared the mechanical arms to secure the drone, but as the sub's lights swept across the depression, something behind the lander reflected a sequence of tiny, organized flashes. At first, they resembled mineral facets catching the beams in slow succession. Then the pattern repeated, this time advancing along the ridge wall as though tracing a path. Water motion alone could not explain it. The movements aligned with the submersible's approach rather than the current sweeping through the channel. One operator suggested that the light might be interacting with thin layers of manganese oxide, which occasionally formed reflective patterns on ridge walls. Another argued that manganese did not typically pulse. Moments later, the instruments monitoring sound captured a series of low notes vibrating through the hull. Such tones were not unusual near active geological sites, yet these were unnervingly regular, separated by equal intervals and rising slightly in pitch with each cycle. The crew paused the retrieval sequence to analyze the pattern, suspecting an approaching shift in the ridge's crust. Slow-spreading zones like this one frequently produced harmonic tremors linked to magma movement, but harmonic tremors rarely produced clean, stepped frequencies. A technician replayed the recording twice, comparing it with archived seismic signatures. None matched. The tones continued steadily, growing more prominent. It was then that the drone's transponder reactivated. After hours of intermittent pulses, its signal sharpened, reforming into a constant beat aligned perfectly with the tone surrounding the vessel. Every person in the submersible recognized the improbability of spontaneous synchronization in failing electronics, yet no plausible alternative surfaced immediately. The drone's pressure logs, visible through the onboard interface, began cycling through their stored data without command inputs. While the team tried to stabilize the feed, the drone's internal lights flickered, illuminating the sediment around it in pale bursts. The ridge walls responded. A faint shift rippled through the basalt towers, sending a soft plume of sediment drifting upward like smoke. Then, the reflective flashes seen earlier intensified, weaving into a pattern that spiraled outward from the depression. The sub snarled against a sudden force tugging it backward, an eddy they thought at first, but its direction contradicted the documented currents at this depth. The engines compensated, but a second stronger pull followed. Lights along the ridge dimmed beneath a spreading cloud of particulate, and the synchronized tones abruptly rose to a sustained, metallic vibration that filled the cabin. Attempts to retreat became impossible. Navigation thrusters fought against an invisible pressure that seemed to compress the water around the hull, tightening in pulses that mirrored the drone's repeating signal. Systems are overloaded in cascading failures, starting with the stabilizers and moving through the mapping software. A final sonar sweep captured one last image, an expanding distortion emerging from the ridge floor, its shape undefined yet unmistakably advancing toward the vessel. The last transmission recorded from the submersible was a single, clipped burst of static that carried the same rising tone echoing through the ridge. The broken beacon of Orpheus Trench. Far beneath the calm expanse of the Aegean Sea, the recovery team dispatched to the Orpheus Trench approached their search with a measured patience shaped by the region's quiet reputation. The deep basin, formed where the African plate descended beneath the Hellenic arc, had long been charted but rarely visited, its steep walls and crushing depths limiting access even to advanced research vessels. Somewhere along one of its shadowed ledges, an emergency beacon had activated in intermittent bursts, signaling a failure of unknown origin. Only a handful of recordings existed from the device, each one distorted and incomplete, but credible enough to mobilize a full recovery expedition. It was an operation intended to gather data, retrieve equipment, and confirm the source of the distress signal. From the moment the submersible began its descent, however, the trench felt more like a place withholding answers than one offering them. Beyond the first layers of descending light, the submersible entered a depth where its instruments began reporting more omissions than readings. Temperature logs held steady, salinity records followed expected patterns, yet sonar returns slipped in and out of coherence as though the water itself shifted between transparency and opacity. The crew anticipated some degree of acoustic distortion. Steep-walled trenches often created shadow zones where sound bent unpredictably, but the extent of this interference surpassed even the most challenging examples documented along the Hellenic arc. Pings vanished before striking the trench walls, and when signals returned, they did so in hollow fragments that carried no sense of true distance. The beacon's pulse remained detectable, but without the echoes normally produced at depth, it behaved like a voice calling into a void. Inside the dim cabin, the crew treated the damaged beacon's shifting signal like a case file requiring careful reconstruction. Standard distress beacons transmitted at regulated intervals, containing identifiers, battery status, and positional data encrypted in short bursts. This one, however, broke its pattern, delivering uneven spacing between pulses and embedding anomalies in its frequency that did not match the effects of pressure or mechanical damage. Specialists compared the intervals across a timeline, expecting the erratic structure to reflect battery decay or internal short-circuiting. Instead, the variations formed subtle groupings, almost rhythmic in their repetition, though not systematic enough to qualify as intentional encoding. The data defied the logic of equipment malfunction, leaving the team to question whether the beacon was responding to conditions the instruments could not yet detect. Along a narrow shelf carved into the trench wall, the beacon emerged on sonar not with a burst of clarity but with a strangely composed stillness. It stood upright, its base resting against a sliver of rock as if positioned deliberately, surrounded by a floor unusually free of sediment for such a depth. the trench typically accumulated fine particulates carried down from the continental slope. Yet here the seafloor appeared swept clean. Sparse ridges radiated outward from the ledge, their contours too smooth to be entirely natural, although no sign of human activity existed in the historical logs for this sector. Visibility improved unexpectedly, revealing the beacon's casing intact and gleaming in the submersible's lights. Whatever distress the device had encountered had not fractured it physically, lending an unsettling contrast to the anomalies buried in its signal. Around the submersible, the acoustic field began behaving with a muted irregularity that did not resemble any known geological interference. The operators noticed it first in the delay between emitted sonar pulses and their returns, a hesitation too slight to register as a malfunction, yet too consistent to ignore. Then came a faint duplication in the recordings, a mirror pulse following each original one by the smallest measurable fraction. Deep-sea environments sometimes produced acoustic reflections from overhangs, tunnels, or dense mineral formations, but the Orpheus Trench lacked mapped cavities large enough to generate such precise mirroring. Each new scan repeated the behaviour, shaping an auditory map that felt incomplete, as though the sub was sensing a presence not fully revealed by its instruments. When the manipulator arms extended toward the beacon, the surrounding water felt unusually heavy, as though resisting each precise movement. The arm's joints vibrated subtly, picking up a resonance that did not correspond to any mechanical strain. Operators attributed the sensation to mineral-rich currents, since dissolved metals and suspended particles could create unfamiliar textures in the water column at extreme depths. Still, the rhythm pulsing through the manipulators did not match the natural circulation of the trench. It throbbed, faintly, almost in sympathy with the beacon's own pulse. Despite the atmospheric unease building inside the cabin, the team proceeded, securing the device and preparing it for retrieval. Throughout the process, the trench remained unnervingly silent. Immediately after the beacon left the ledge, a sudden absence swept through every returning signal, quiet and absolute. Sonar mapping screens dissolved into uniform darkness, bathymetric outlines flattened, and even the low, ever-present hum of distant tectonic activity ceased without transition. The silence did not resemble equipment failure, rather it mimicked the effect of transmitting into open air, where no medium existed to carry sound back. For a single moment, an image appeared on the display, a perfectly smooth, vertical return extending the full height of the trench wall near their position. No natural formation produced such geometry, and the signature lacked the texture characteristic of bedrock. The reading vanished after one pulse, leaving the crew uncertain whether they had captured a real structure or an artifact created by the collapse of acoustic feedback. Far above the rising silt, the ascent slowed as the sub encountered a zone where sound vanished into the dark without a single echo. This effect was known in undersea volcanic regions, where porous rock absorbed sonar waves, but the geological maps of the Orpheus Trench showed no such deposits in this section. The sub fought to maintain orientation as fragments of static threaded through its communication link with the surface. Through the haze of interference, one final reading emerged from inside the cabin's monitoring console. The beacon's pulse, which had gone silent during retrieval, reactivated without warning. Only this time, its signal originated from somewhere above the submersible rather than from within its secured container. No one aboard could explain how the pulse had moved, or why the interval between bursts had settled into a perfect, unchanging rhythm. Something in the unseen corridors of the trench answered with a patient clarity that no beacon should ever possess. The ghost pods of the Aotssk shelf. On a morning veiled in pale subarctic light, the expedition team gathered on deck to review unexpected sonar anomalies that had appeared along the northern stretch of the Aotssk shelf. The vessel, outfitted for deep-sea recovery in extreme cold, had been monitoring a section of the continental margin known for its seasonal sea ice and methane hydrate deposits. The anomalies had first appeared during a routine mapping survey, and analysts had been unable to reconcile their shape or behaviour with any documented geological or biological feature. The team's mission was to retrieve a cluster of unidentified pods recorded in the affected sector, equipment that had defied conventional identification for reasons no scientist could yet explain. Notes from previous dives indicated that the pods were metallic, silt-coated, and stable on the seabed. yet the latest acoustic signatures suggested a subtle drift, movement unaccounted for by known currents or subaqueous forces. As the vessel drifted above, the continental margin unfolded in long terraces of silt and volcanic debris, moulded by millennia of tectonic shifts. The Aotssk shelf, while relatively shallow compared with true abyssal plains, featured steep drop-offs and fissures carved by glacial scouring and tectonic activity. The submersible, equipped with high-resolution cameras and manipulator arms, navigated over terraces blanketed in fine sediments, each layer revealing a record of seasonal productivity, plankton blooms, and suspended detritus. The anomaly's location corresponded to a small depression near a methane seep, an environment that can produce localized turbidity and chemical gradients, yet none of these conditions explained the apparent placement of the metallic pods. Every scan returned objects that seemed deliberately oriented, suggesting human intervention, or something far less understood. On their monitors, the signature appeared again with stubborn clarity, as though the seabed itself were broadcasting a pattern that demanded attention. Playback from the previous expedition revealed a single pod, its surface etched with concentric scratches inconsistent with natural abrasion. Its outline rested at a precise angle, suspended slightly above the sediment layer as though supported by invisible forces. Acoustic logs recorded subtle harmonic pulses around the object, minor oscillations that conventional physics could attribute to current drag or submersible turbulence, yet the sub remained motionless during recording. These faint vibrations hinted at something unusual beneath the pod's base, something dense enough to transmit a measurable resonance through the sediment. Within the briefing room, the atmosphere grew taut as geologists traced the anomaly's outline and noted its unsettling symmetry. Unlike the random scatter of rocks and boulders typical of the continental shelf, the pod's geometry aligned with others found nearby. A second pod appeared partially buried, its sides reflecting the sub's lights with a dull sheen, while sediment around its edges remained remarkably undisturbed, except for a shallow trench that suggested recent displacement. Records of benthic life were cross-referenced. Snow crabs, polycate worms, and benthic jellyfish were present, yet the distribution patterns implied an abrupt disturbance shortly before observation. The juxtaposition of biological stasis and artificial alignment made it difficult to classify the site as either natural or entirely anthropogenic. When the recovery submersible finally descended toward the marked coordinate, its floodlights carved thin corridors of visibility through these suspended particulates. The cold, near-freezing water slowed sediment suspension, allowing every detail to be captured in high-definition footage. The sub moved carefully over a subtle slope, its path intersecting a small cluster of pods, each partially embedded yet seemingly aware of the vehicle's approach. Fine sediment shifted around the pods as if the ground itself had yielded momentarily, only to settle perfectly afterward. Instruments measuring conductivity, salinity, and temperature detected nothing abnormal in the water column, yet the harmonic resonance surrounding the pods persisted, as though they maintained a synchronized vibration independent of environmental conditions. Closer to the seafloor, the landscape revealed itself in muted layers of sediment interrupted by the shapes that would later be called ghost pods. Each object, roughly cylindrical and capped at both ends, bore slight differences in corrosion, suggesting varied material composition or age. One pod tilted forward gently, as though adjusting to the submersible's proximity. Analysts noted that the phenomenon did not match patterns produced by benthic currents in the Okhotsk shelf, whose winter flows generally move southwest at a steady but slow pace. The drift of the pod and its angular adjustments, though subtle, appeared deliberate, a motion counter to both expectation and physics, recorded precisely in the sub's high-frequency acoustic data. Minutes into the survey pass, the pilot noticed the first of the structures tilting beneath its own weight, as though burdened by centuries of pressure. Manipulator arms were extended for recovery, and on contact, the pod emitted a low, almost imperceptible vibration. Typically, interactions with metallic objects produce reverberations tied to hull contact or water drag, yet this vibration persisted even when the sub's engines idled. The team paused to reassess, checking all mechanical systems and environmental sensors, confirming that the effect originated from the object itself. As the pod was gently lifted, the vibration ceased abruptly, leaving an unnerving silence that the sub's acoustic sensors could not penetrate. Past that fragile cluster, the cameras revealed dozens more, their arrangement defying any natural current. Many pods lay partially covered in sediment, but their alignment suggested placement in deliberate rows. Some bore striations matched no known tool or marine process, and faint reflections from their surfaces created the illusion of movement, though repeated video analysis confirmed that no currents could have produced it. When the sub emitted low-frequency pings, some returned echoes slightly ahead of schedule, as if the pods themselves were transmitting or responding to the sonar. In the control cabin above, the mission analysts watched the live feed in unsettled silence as faint reflections pulsed from within some of the pods. The interior details were obscured by sediment and condensation, yet patterns of light suggested internal cavities that did not correspond to conventional storage pods or pressure containers. Attempts to retrieve them were met with subtle resistance, a phenomenon without precedent in similar deep-sea recovery operations. Every movement, every ping seemed to trigger a responsive adjustment in the pod's position, although no propulsion or external force could be detected. As the submersible manoeuvred for a closer view, its sensors began returning erratic depth readings that shifted by meters in a matter of seconds. The log suggested either instrument malfunction or interference from the pods themselves. In the seconds before ascent, one pod, previously still, rotated slightly in the water column as if observing the vehicle. By the time the team completed the dive, the remaining footage left questions unresolved. The pod's drift, their subtle vibrations, and their inexplicable alignment defied both physics and expectation. Analysts catalogued every anomaly, but no single explanation emerged to account for what they had witnessed. In that drifting glow, something indistinct moved behind the final pod, as though waiting for the lights to dim. The black silos of the Scotia abyss. Anomalies first appeared in the sonar logs as faint vertical blips that refused to match any known topographic feature, prompting the Scotia Abyss expedition to plan a direct investigation. Analysts had noticed the irregular returns during routine mapping of the abyssal plain, an area shaped by the Antarctic circumpolar current and overlying the Scotia plate. The blips suggested structures rising sharply from the sediment, but their form, alignment, and density defied comparison with any documented abyssal formation. The mission's primary goal was to investigate these anomalies in detail, document their dimensions, and determine whether they were geological, biological, or something altogether more enigmatic. The crew approached the task with meticulous caution, aware that the depth, between 5,000 and 6,000 meters, meant that the submersible's instruments and mechanical arms would be pushed to their limits. Subsequent sweeps revealed dark silhouettes rising sharply from the sediment, each standing with an unnerving uniformity that defied natural erosion. Sonar imaging displayed a series of cylindrical structures spaced with apparent regularity, their bases embedded in fine silt while their upper faces extended vertically into the abyssal darkness. Abyssal plains typically show uneven sediment accumulation, with occasional volcanic pinnacles or sediment mounds appearing randomly. Yet here, the formations were consistently similar in height and diameter, suggesting either an extraordinary geological process or an arrangement that hinted at design. Even minor variations in the slopes of adjacent formations seemed deliberate, as though each structure had been placed to interact with its neighbours. During the submersible's descent, its instruments recorded temperatures just above freezing and currents twisting unpredictably around the looming structures. The Scotia Abyss is influenced by the Antarctic circumpolar current, known for its strength and turbulence, yet near the silos, the water column moved in unusual laminar flows along certain faces. Fine particulate matter drifted slowly, suspended in the near-freezing water, allowing the sub's lights to illuminate the black columns in stark relief. Pressure readings confirmed the expected 500-600 atmospheres, yet nothing in the environmental sensors indicated a natural explanation for the near-perfect verticality of the silos. Detailed measurements indicated the tallest silo stretched nearly 50 meters from base to summit, with faces so smooth they reflected the sub's lights in muted streaks. The diameters were consistent, averaging 8 to 10 meters, and bases were set firmly in the abyssal silt. The surface reflected light in a way atypical for basalt pinnacles, suggesting that either erosion had polished the exterior unusually, or the material was different from the surrounding volcanic deposits. Geologists compared the structures with known formations in the South Sandwich Trench, noting that natural basalt columns rarely exceeded 20 metres in height with such uniformity. These silos presented a scale and precision that raised questions about their origin, though no human intervention could account for their presence at such depths. High-resolution photographs revealed striations along vertical faces, resembling basalt columns, yet the repetition and spacing of the silos exceeded any known geological example. Each column bore fine linear patterns consistent with cooling fractures, but the spacing between adjacent silos was almost identical, forming near-perfect rows across the abyssal plain. Some appeared hollow, yet pressure sensors detected no large internal cavities, suggesting solid rock or dense mineral content. The photographic record offered a surreal perspective. From certain angles, the silos appeared as a black city emerging from the sediment, their shadows stretching far into the abyssal gloom. Observations of current and sediment behaviour showed that some faces remained nearly bare, despite the surrounding abyssal flows stirring fine particles elsewhere. Typically, sediment accumulation covers irregularities over decades or centuries, but the silo's surfaces suggested that currents were deflected in a way that left some faces exposed. Turbulence maps showed minor eddies along the edges, yet these could not fully explain why the vertical faces were free of silt while the surrounding areas were blanketed. The combination of smoothness, height, and orientation created an optical effect in the sub's lights, giving the impression that the silos were both monolithic and impossibly precise. Magnetometer readings registered subtle, unexplained variations near the tallest structures, suggesting density irregularities hidden beneath the solid exterior. The variations were minor, not indicative of metallic objects, but enough to produce readings inconsistent with solid basalt alone. Sonar reflections also behaved peculiarly. The upper sections returned clear echoes, while the bases, embedded in sediment, produced distorted signals. The anomalies persisted even when the sub remained stationary, as though the structures themselves influenced the surrounding physical field. Scientists noted that no known abyssal formations of this scale or composition exhibited similar characteristics. When compared with other abyssal pillars across the South Atlantic and Scotia Sea, the alignment and repetition of these formations appeared almost intentional, challenging conventional explanations. Geological records show volcanic pinnacles and basalt columns forming in clusters, but randomness dominates. The Scotia abyss silos formed parallel arrays spanning hundreds of meters, each nearly identical in height and spacing. Patterns continued beyond the mapped area, suggesting that the structures extended farther than the expedition could initially chart. The impossibility of natural processes producing such uniformity reinforced the sense of quiet mystery enveloping the survey. Approaching the base of the largest silo, the sub recorded subtle vibrations along its hull, their source neither mechanical nor natural. The effect was subtle. A low-amplitude hum felt more than heard, and persisted even when the submersible ceased all movement. Attempts to reconcile the readings with local tectonic activity or underwater currents failed. Cameras captured nothing unusual, but the sensation of resonance heightened the tension, as though the silos themselves were responding to the presence of the vessel. No known formation at such depth had ever exhibited such interaction with human equipment. Final imagery captured the complete array of silos, their shadows stretching across the abyssal plain in patterns that hinted at order beyond natural chance. Mapping overlays confirmed spacing regularity, while sedimentation and current patterns did not explain the exposed surfaces or mirrored alignment. Data logs contained all measurements, acoustic readings, and photographs, yet none offered a definitive conclusion. Analysts could only speculate, leaving the expedition with questions deeper than the abyss itself and a growing awareness of the unknown forces that might have shaped these monolithic formations. And somewhere in the crushing darkness beyond the sub's lights, the black silos seemed to stand in silent alignment, waiting for some presence that had yet to arrive. The frozen wreck of Station Aurelia. Faint blips on satellite-linked sonar had drawn the expedition team's attention, suggesting the long-lost Station Aurelia might finally be within reach of investigation. The station, a polar research facility last confirmed in operation decades earlier, had vanished from communications without explanation. Its coordinates, mapped during brief seasonal resupplies, placed it on the continental shelf beneath perennial sea ice in one of the planet's most hostile environments. Experts on board the research vessel meticulously planned the approach, aware that extreme temperatures, shifting ice, and high-pressure waters would challenge every system in the submersible. The expedition aimed not only to document the wreck, but to gather insight into the station's sudden disappearance, preserving both scientific and historical evidence before the harsh environment could reclaim it entirely. Initial scans revealed a fragmented outline partially buried in ice and sediment, the signature unmistakably human yet twisted by decades of sub-zero currents and shifting ice. Sonar images displayed angular shapes interspersed with scattered debris, some partially hidden beneath layers of sediment that had settled over decades. The surrounding terrain of the Antarctic continental shelf was composed of uneven silt plains, punctuated by ridges formed during glacial advances. Water temperatures hovered just above freezing, and the slow movement of suspended ice crystals gave the images a ghostly blur. Even in the early scans, the station's remains suggested both sudden collapse and slow submersion, leaving observers uncertain where natural processes ended and human-made structures began. As the submersible descended through near-freezing waters, instruments strained against extreme pressure while the vehicle navigated around suspended ice crystals and uneven seabed slopes. Hull thermometers recorded temperatures barely above 1 degree Celsius, while manipulator arms extended carefully to avoid disturbing fragile modules. Pressure sensors confirmed readings approaching 220 atmospheres, a constant reminder of the depth's lethal potential for equipment and crew alike. Navigation relied on inertial measurement and sonar mapping, as visual cues were obscured by both particulate matter and darkness. Each meter downward revealed subtle changes in sediment composition, evidence of seasonal meltwater deposits and microcurrents unique to this polar region. The first modules came into view: twisted steel, insulation panels partially sheared away, and scattered equipment marking the station's final resting place. The main lab section leaned at a sharp angle, suggesting either a structural failure or a gradual collapse into a soft sediment layer. Observation ports were fractured, and external panels bore the scars of ice abrasion, consistent with the seasonal drift of nearby icebergs. Despite the wreck's damaged state, certain modules remained surprisingly intact, providing a glimpse into the station's original configuration. Onboard engineers noted the presence of reinforced steel beams designed to withstand ice load, yet several had bent under circumstances that could not be explained solely by environmental stress. Surrounding the wreck, unusual sediment patterns and small icebergs hinted at forces beyond ordinary currents, with debris subtly shifted in ways difficult to reconcile with natural motion alone. Sediment cores taken near the modules revealed layers compacted in irregular patterns, possibly due to the station's gradual settling or minor undercurrents deflected by the structure itself. Small fragments of equipment, some weighing hundreds of kilograms, lay partially embedded in the seabed at odd angles. Oceanographic data confirmed that Antarctic bottom water flows were steady and cold, yet these currents could not have caused such precise displacement or apparent clustering of debris. The combination of environmental forces and human artifacts created an eerie scene, a station suspended between natural processes and an unknown cause of collapse. Inside the intact compartments, frozen machinery, dampened instruments, and partially preserved logbooks offered glimpses into the station's operational life and abrupt abandonment. Power units and battery housings were coated in mineral deposits but retained their basic structure. Communication arrays, though bent, retained fragments of wiring, and partial records from weather monitoring instruments remained legible. Researchers speculated that the abrupt cessation of operations left many systems powered down mid-cycle, effectively freezing a moment in the station's final days. Each interior observation reinforced the dual sense of historical documentation and unresolved mystery, as though Station Aurelia had recorded its own disappearance without explanation. Several structural distortions caught the team's attention: warped hull panels and bent beams that suggested an extraordinary stress beyond the pressure of ice and water alone. Calculations of expected ice load indicated that the station should have remained largely upright, yet some sections had collapsed inward while others appeared twisted or sheared. The pattern of deformation did not correspond to any known iceberg impact or seasonal freeze-thaw cycle. Structural engineers on board debated whether sudden sub-ice movement, internal mechanical failure, or some other unidentified force could account for the anomalies. The station's design, intended to endure extreme conditions, had been compromised in ways that remained partially inscrutable, even to experienced observers. Sensors picked up faint echoes within the modules, subtle vibrations inconsistent with submersible movement or natural acoustic reflections, lingering as if the station itself remembered the past. Low-frequency sonar returned minor reverberations that shifted slightly in timing and intensity, yet no mechanical sources were present. The effect was transient but measurable, enough to cause crew members to pause and reconsider the environment surrounding the wreck. Water conductivity and temperature readings remained consistent, eliminating most conventional explanations. Even in the sterile cold of the abyss, the submersible's instruments suggested an echo of history embedded within the station's remains. Final sweeps recorded the orientation of the wreck and its scattered artifacts, leaving data that confirmed both the station's human origin and the mysteries embedded in its sudden collapse. Photographs captured the modules from multiple angles, noting intact panels, bent steel, and sedimented equipment. Logs of sonar returns, pressure readings, and water chemistry completed the dataset, providing a permanent record for analysis long after the submersible returned to the surface. Yet despite meticulous documentation, questions persisted. Why certain modules had shifted, what had caused specific fractures, and whether the station's abandonment had involved more than environmental stress. The wreck had become a frozen enigma, preserving both fact and unanswered question. The submersible's slow ascent revealed nothing new, yet the team recorded each anomaly with precision, knowing many secrets of the frozen wreck would remain elusive. The return journey offered a slow reflection on the station's history, the harsh environment, and the stubborn mysteries that had preserved its final state. Each layer of ice and sediment told part of a story, yet gaps remained where no data or observation could penetrate. Even with modern instruments and expert interpretation, the wreck refused to yield all its secrets, maintaining a silent presence in the depths of the polar shelf. Locked away in ice and sediment, Station Aurelia held its secrets, impervious to any instrument or observer. The last signal from the Bailion vault. The Bailion vault had been built decades earlier to store deep ocean research data, and its sudden silence had puzzled marine scientists ever since. Originally constructed as part of a series of deep-sea monitoring installations, the vault lay along a remote section of the continental slope, several hundred kilometers from the nearest research vessel. Its primary purpose had been to house sensitive oceanographic recordings, seismic data, and climate measurements, all stored in reinforced modules designed to withstand crushing pressures and near-freezing temperatures. For years, the vault transmitted intermittent updates to surface stations, but then, without warning, all signals ceased. The expedition now aimed to locate the facility, examine its condition, and recover whatever information remained intact, fully aware that decades underwater could have changed everything. Early sonar sweeps and signal scans revealed faint echoes and pings that resisted conventional interpretation, suggesting both depth and obstruction were complicating detection. The echoes were irregular, shifting slightly in amplitude and timing as the submersible maneuvered through the slope's uneven topography. Local sediment, sculpted by Antarctic bottom water currents, created a landscape of ridges and depressions that complicated sonar reflections, producing ghost images that could be mistaken for man-made structures. Yet careful analysis indicated a pattern consistent with the vault's known dimensions: rectangular outlines, grouped modules, and faint linear extensions that could correspond to cables or sensor arms. The precision of these echoes stood in contrast to the randomness of the surrounding seafloor. Into the darkened depths, the submersible's instruments tracked rising pressures and icy temperatures, conditions that warped both sound and electromagnetic signals. Hull stress gauges registered gradual compression under the immense weight of water, while navigational thrusters had to compensate for subtle, unpredictable currents. Even minor adjustments could create cascading effects on the sub's positioning, potentially altering signal reception. Acoustic waves propagated more slowly through the dense, cold water, and electrical signals attenuated rapidly, making it difficult to maintain a continuous link with the vault or even confirm its exact location. Every metre of descent reinforced the isolation of this buried archive, suspended in a world the human body could never endure without machinery. Initial capture of digital pulses and fragmented acoustic transmissions hinted at data partially preserved within the vault, yet intermittent gaps left critical details obscured. Recordings from the vault's onboard logging system appeared as short bursts of binary sequences, separated by long intervals of silence or distortion. Attempts to decode the signals revealed portions of environmental measurements, yet large swaths of data were incomplete or corrupted. The faint persistence of these transmissions indicated that at least some modules retained limited power, perhaps through residual batteries or decayed capacitors, but the exact mechanisms were uncertain. Even in their fragmented form, the signals provided a haunting sense of the vault's ongoing presence, quietly broadcasting its existence across the dark ocean. Visual observation confirmed the vault's reinforced modules, sensor arrays, and external housings, oriented with precise alignment against the ambient deep-water currents. Each module bore signs of decades submerged: corrosion along edges, mineral incrustations, and small fractures from repeated thermal and pressure cycles. Sensor arms protruded at angles consistent with deployment records, yet several were bent or partially buried in sediment, evidence of subtle shifting over time. The module's reinforced steel frames glinted dimly under the sub's lights, revealing construction designed for durability, but now silently succumbing to the ocean's slow, unrelenting processes. Even at a distance, the vault's form suggested both human engineering and the immense scale of isolation it had endured. Analysis of the distorted signals revealed frequency shifts and unexpected interference patterns, inconsistent with known physical phenomena at these depths. The submersible's instruments measured small anomalies in wave propagation, suggesting reflections or modulations that could not be traced to nearby terrain or natural currents. Magnetometer readings were largely stable, yet faint fluctuations appeared in certain orientations, hinting at localized conductivity variations. Acoustic echoes sometimes returned signals milliseconds ahead or behind expected timing, an effect that the crew logged meticulously, noting the irregularities without reaching a clear explanation. These subtle deviations contributed to the growing sense that the vault's final transmissions carried a message partly obscured by the ocean itself. Attempts to interface the submersible's instruments with the vault yielded brief but unstable connections, highlighting both the fragility of the equipment and the vault's unyielding isolation. Robotic arms extended toward junction panels, securing temporary links to probe data ports. Each connection lasted mere seconds before signals failed, yet during these fleeting moments, the crew could retrieve fragments of archived measurements and operational logs. Even small bursts of information required careful decoding, as environmental conditions distorted both voltage and frequency. The ephemeral success of these attempts underscored the difficulty of retrieving knowledge from a location so far removed from direct human intervention. Strange fluctuations in background noise and subtle electromagnetic anomalies appeared during these probes, defying straightforward explanation despite careful logging. Low-level hums and transient pulses seemed to originate from within certain modules, although no active systems remained powered. These signals interacted unpredictably with the submersible's own instruments, creating interference patterns that were logged but remained unexplained. Minor water movements or magnetite deposits could account for some readings, but the timing and regularity of the anomalies suggested a source beyond conventional environmental factors. The effect was brief, almost imperceptible, yet it contributed to a pervasive sense that the vault retained an echo of the human activity that had once animated it. The final recorded signal reached the submersible in fragmented form, a haunting echo of data that hinted at information lost forever in the abyss. Binary sequences appeared for a few seconds before dissolving into silence, leaving patterns that researchers could only partially reconstruct. Some fragments suggested environmental readings or internal system logs, while others hinted at warnings or maintenance sequences incomplete at the moment of transmission cessation. The team carefully documented each fragment, aware that the vault's final messages had been preserved, but were fundamentally inaccessible, trapped in the water column and the layers of sediment that surrounded the structure. With each meter gained in the ascent, the team recorded observations and partial transmissions, aware that some uncertainties about the vault could never be resolved. Detailed records included sonar maps, signal logs, visual imagery, and environmental data, yet gaps persisted that no instrumentation could bridge. The experience left the crew with a heightened awareness of both the ocean's depth and the limits of human understanding. Each fragment of the vault's last communication spoke of knowledge, effort, and perhaps warning, but the full story remained veiled beneath kilometers of water and years of silence. Out of reach and shrouded in darkness, the Bailion vault preserved its secrets, offering only fragments of a story no instrument could capture completely. The vanished capsules of the Celtic deeps. The expedition had descended into the Celtic deeps to retrieve environmental monitoring capsules deployed years earlier, their exact locations charted but unverified for decades. These capsules, cylindrical and reinforced, had been part of a network designed to measure temperature, salinity, and microcurrents at extreme depths, contributing to long-term studies of ocean circulation and climate patterns. While the original deployments had been meticulously documented, time and the shifting seabed rendered the precise positions uncertain. The team approached the mission with both scientific rigor and a sense of caution, knowing that the combination of depth, pressure, and unpredictable currents could complicate the recovery of objects so small and isolated. Each member of the crew understood that even minor miscalculations could result in lost data or equipment, yet the potential rewards of rediscovering these capsules outweighed the risks. Initial sonar sweeps painted a patchwork of the seafloor, where ridges and trenches complicated efforts to pinpoint the small, cylindrical objects amid layers of sediment and detritus. The Celtic deeps, reaching depths of over 3,000 meters in some areas, presented a landscape of narrow troughs, uneven sediment plains, and scattered rock outcrops. Low-frequency sonar provided broad coverage, while high-resolution multi-beam systems sought the subtle outlines of the capsules. Despite the precision of modern equipment, the uneven seabed distorted acoustic returns, producing echoes that were difficult to interpret. The team adjusted the scan angles, recalibrated the instruments, and painstakingly reconstructed the seafloor in digital maps, hoping to reveal the familiar shapes of the capsules among the natural formations. After hours of searching, the crew confronted an unsettling reality. The capsules were gone, leaving no sign of their intended resting positions and no immediate explanation for their disappearance. Their last known coordinates had been confirmed by previous expeditions, and even accounting for minor shifts in sediment, the objects should have remained detectable. Yet repeated sweeps yielded nothing conclusive. The absence was not merely a matter of poor visibility or instrument error. The capsules had vanished in a manner that suggested a sudden or unexplained displacement. For scientists who had tracked these instruments for years, the disappearance raised questions about forces in the deep sea that could remove well-engineered devices without leaving clear traces. Oceanographic measurements suggested strong, shifting currents and occasional turbidity flows, yet these forces alone seemed insufficient to account for the total absence of the capsules. The team recorded current speeds, temperature gradients, and salinity profiles, noting that while the Celtic deeps experienced episodic surges, they were rarely strong enough to transport objects weighing several kilograms without dragging them along predictable paths. Sediment cores taken nearby indicated relatively undisturbed layers, further complicating the explanation. The discrepancy between expected and observed positions of the capsules suggested that other, unmeasured variables might have contributed to their disappearance. Fragments of buoyancy modules and tethering cables hinted at partial failures, revealing the engineering of the capsules while offering only partial clues to their ultimate fate. These remnants, small and scattered, confirmed that some of the objects had experienced physical stress or degradation over time. The capsules had been constructed from high-strength polymers and corrosion-resistant alloys, designed to survive years under crushing pressures exceeding 300 atmospheres. Their flotation components, intended to maintain orientation and stability, appeared partially detached in certain fragments, suggesting a mechanical failure or impact event, yet the majority of the capsules remained unaccounted for, their absence magnified by the contrast with these scattered traces. The ROVs swept the area with cameras and manipulator arms, documenting subtle disturbances in the sediment and clusters of small debris that hinted at movement inconsistent with known current patterns. Video feeds revealed depressions and displaced sediment layers that appeared recent, yet their origin was unclear. The submersible's manipulator arms probed carefully, avoiding further disturbance while attempting to locate any identifiable portions of the missing capsules. The team recorded every anomaly, noting the irregular distribution of fragments and the subtle shifts in surrounding materials that could suggest displacement by forces beyond ordinary oceanic motion. Scientists aboard the vessel debated possible explanations, weighing natural drift, mechanical failure, and unknown forces that might have displaced the capsules far from their predicted coordinates. Comparisons were drawn to historical deep-sea deployments, where currents and sediment slides occasionally moved instruments, yet rarely in such a complete or untraceable manner. The discussion remained open-ended, as no single hypothesis fully reconciled the physical evidence with the documented positions and construction of the capsules. The combination of environmental factors and engineering resilience created a puzzle that refused to yield a definitive solution. Patterns in sediment displacement and the scattered positions of minor artifacts defied conventional physics, leaving investigators with measurements that contradicted all standard models of deep-sea movement. Certain depressions appeared too precise and isolated to result from natural flows, while other clusters of debris suggested localized disturbance with no apparent origin. The team meticulously logged these anomalies, comparing them to hydrodynamic models and known geological processes. Even the smallest variations in particle orientation or accumulation were recorded, each one a subtle clue that hinted at an invisible force at work beneath the waves. Attempts to recover the remaining fragments faced relentless environmental challenges: low visibility, suspended sediment, and unpredictable currents that rendered each maneuver precarious. The ROV's manipulator arms could secure only a fraction of the scattered materials, while cameras documented the broader field for post-expedition analysis. Every movement risked stirring sediment, obscuring visibility further, and potentially shifting other fragments. The crew worked with deliberate care, aware that one misstep could erase crucial evidence, yet despite these efforts, the majority of the capsules remained missing, their precise whereabouts a stubborn mystery of the deep. By the end of the survey, the crew had compiled meticulous records yet could not resolve the mystery, leaving the disappearance of the capsules as one of the Celtic Deep's enduring enigmas. Maps, video recordings, sediment analyses, and environmental data provided a comprehensive account of the area, yet they only deepened the questions surrounding the vanished objects. The expedition departed with a mixture of accomplishment and frustration. They had documented the scene in unprecedented detail, but could not recover the instruments that had inspired the investigation. The Celtic Deeps had preserved their secrets, leaving behind only fragments and questions. The shadowed trenches and ridges concealed the vanished capsules, leaving their purpose and location a mystery lost to the depths. The shattered lander near Reikis Ridge. During the summer expedition of 2023, the research vessel Oceanic deployed a geological lander near the Reikis Ridge, aiming to capture hydrothermal vent activity and seafloor geochemistry. The lander, weighing nearly 3 tons and equipped with pressure-resistant sensor modules, had been designed to operate at depths exceeding 3,000 meters. Its mission included recording temperature gradients, mineral deposition, and microseismic activity along one of the Mid-Atlantic Ridge's most geologically active segments. Scientists had carefully plotted deployment coordinates to coincide with known vent fields and previously mapped basaltic fissures. Decades of prior research had shown that instruments at these depths could remain functional for extended periods, but the Reikis Ridge presented unpredictable conditions that challenged even the most advanced equipment. The lander plunged deeper, recording crushing pressures and icy temperatures that challenged every system and heightened crew awareness. The submersible platform monitored the descent carefully, logging depth increments and current velocities. The ridge's underwater topography, carved by tectonic forces and volcanic activity, created turbulent flows that buffeted the descent. Thermocline variations and suspended particulate matter further complicated telemetry, and the crew adjusted thruster output and stabilizing fins to maintain the lander's orientation. Every meter of descent reinforced the sense of isolation inherent in deep-sea operations, where even minor miscalculations could have irreversible consequences. Upon reaching the ridge floor, initial visual scans revealed the complex topography of basaltic ridges, sediment-covered fissures, and the faint plumes of hydrothermal vents that dotted the area. The lander settled on a sloping section of basalt, partially surrounded by vent chimneys emitting mineral-laden water at temperatures exceeding 350 degrees Celsius at their cores. Sediment layers were thin but uneven, covering irregular rock formations and small debris fields from past eruptions. ROV cameras transmitted live footage, capturing the stark contrast between the cold, dark water and the occasional glimmer of mineral deposits. These visuals confirmed that the lander had arrived in the expected location, yet the environment appeared more dynamic and turbulent than models had predicted. Closer inspection quickly revealed that the lander's manipulator arms were bent and several sensor modules had been torn free, damage exceeding what engineers had predicted for normal deployment stress. Hydraulic lines were kinked, protective housings cracked, and wiring partially severed. Small fragments of metal and insulation littered the immediate vicinity, suggesting sudden impact or torsional force. Engineers on board compared the observed damage with stress tests conducted in deep-water simulation tanks, finding that the forces required to produce such breakage far exceeded normal operational loads. The lander's resilience had been compromised, leaving much of its mission unfulfilled and its instruments only partially functional. Data suggested turbulent microcurrents around the ridge and intermittent hydrothermal bursts, yet even combined, they seemed insufficient to explain the wreckage. Temperature and flow sensors recorded abrupt shifts in velocity and direction near vent outlets, yet calculations indicated that even the most forceful bursts would not generate enough stress to bend reinforced manipulator arms or fracture housing modules. Sediment cores and current profiling revealed localized turbulence and scouring, but the scale of disruption remained inconsistent with observed damage patterns. The team considered whether multiple contributing factors, a minor underwater landslide, vent surges and localized eddies, could have combined to create such extreme conditions, but no definitive evidence emerged. Technical review of pre-deployment logs and structural schematics confirmed the lander had left the ship fully operational, with no signs of malfunction before descent. Pressure tests, battery health, and sensor calibration records all indicated readiness for the mission. Deployment protocols had been followed precisely, including orientation stabilization and tether checks. The absence of pre-existing mechanical flaws narrowed the possibilities for the damage to external environmental forces rather than internal failure. Yet even with this assurance, the magnitude of the destruction suggested phenomena that the expedition had not anticipated, highlighting the unpredictable nature of mid-ocean ridge environments. The team debated possible scenarios, considering the tectonic microquakes, sediment flows, or even collision with previously unmapped debris, yet each explanation left unanswered questions about the nature of the event. Seismic monitors detected low-level tremors in the ridge region, consistent with normal tectonic activity, but not enough to produce a catastrophic mechanical impact. Debris fields from past eruptions were mapped in surrounding sectors, but trajectories and elevations did not align with the lander's final position. Each hypothesis accounted for some but not all observations, leaving the crew to piece together a complex puzzle with too many missing variables. From the moment it descended, the ROV faced challenges: swirling vent currents, shadowed waters, and shattered modules teetering on sharp basalt formations. Manipulator arms were extended to retrieve intact sensor housings, but strong microcurrents shifted the sediment, concealing smaller fragments. The ROV's thrusters created additional turbulence, necessitating careful maneuvering to avoid further damage. Each recovery action required balancing operational precision with environmental awareness, yet despite meticulous effort, several critical modules remained inaccessible, their data potentially lost to the depths. Data retrieved from partially functioning instruments revealed brief, irregular bursts of hydrothermal readings interspersed with corrupted sequences, suggesting the lander experienced sudden mechanical shocks at depth. Temperature spikes, mineral flux measurements, and pressure anomalies appeared intermittently, punctuated by long gaps of missing or garbled data. Scientists examined timestamps, cross-referencing environmental observations and seismic logs, hoping to correlate readings with specific destructive events. The irregularities hinted at sudden high-energy interactions, yet no sequence fully explained the lander's compromised condition. By the conclusion of the expedition, investigators had reconstructed only fragments of the incident, leaving much of the lander's destruction and the forces responsible unresolved. Sonar mapping, visual surveys and recovered instrument readings offered partial insight into the violent encounter, but the true sequence of events remained obscured. The Reikis Ridge's dynamic environment, a combination of hydrothermal turbulence, tectonic instability and unpredictable currents, had produced a scenario that no model could fully replicate. Even as the crew departed, the shattered lander lay scattered across the basalt slopes, a testament to both human ambition and the ocean's capacity for sudden inscrutable violence. Amid the jagged ridges and venting fissures, the shattered lander remained, a witness to secrets the ocean had long concealed. The silent hall of the Pelos Shelf. The Pelos Shelf stretched into shadowed depths, where steep submarine canyons carved the seabed, and the recovery vessel hovered above, poised to retrieve monitoring containers. These containers had been deployed years earlier to collect data on currents, salinity and nutrient levels across the Ligurian Sea, forming part of a broader study on Mediterranean deepwater circulation. Their retrieval was routine in theory, a carefully documented position, modern ROVs with manipulator arms and redundant communication lines. Yet the environment beneath the surface was far from predictable. The shelf's steep gradients, interlaced canyons and variable sediment layers made even a standard recovery a challenge that demanded precision, patience and constant vigilance. Currents twisted along the shelf, carrying fine silt and drifting debris that swirled in slow eddies around the descent path of the ROV and its tethered equipment. Instruments measured subtle fluctuations in flow speed and direction, revealing localized turbulence that could interfere with positioning or obscure visual feeds. Suspended particles reduced visibility, creating faint drifting veils that altered the perception of depth and distance. Every meter of descent required continuous adjustment, as the ROV's thrusters compensated for both predictable tidal flow and unexpected surges. These microcurrents, invisible on surface charts, shaped a labyrinth of motion that could carry objects, sediment, and even debris far from their original resting points. Sonar scans revealed the hull resting in a small depression, half buried in sediment and framed by jagged outcrops that funneled water into unseen channels. The containers appeared intact from above, yet the uneven terrain raised concerns about accessibility and stability. The surrounding sediment consisted of fine silt interspersed with coarser grains, forming small ridges and mini-troughs that could trap objects displaced by currents or equipment interaction. Mapping the immediate area revealed subtle depressions and raised surfaces, a hidden topography that challenged expectations and demanded careful navigation to avoid disturbing the seabed unnecessarily. Flickering images from the ROV cameras revealed unusual reflections on the container's surfaces, hinting at movement or partial submersion that the instruments had not anticipated. Small scuffs and discoloured patches suggested abrasion against rock outcrops, while subtle sediment plumes indicated recent shifts in position. The operators noted that the containers were not as stable as the original deployment had indicated, raising questions about whether natural forces had slowly altered their resting place. Each frame was examined with attention to the faintest hints of disturbance, as even minor shifts could suggest larger, unseen forces acting beneath the water. The operators navigated carefully, adjusting thrusters to counter the unpredictable flow, while attempting to secure the containers with manipulator arms that trembled under subtle pressure shifts. The tethered ROV swayed slightly as eddies brushed against its hull, making precise maneuvers difficult. One container seemed to tilt slightly when grasped, prompting immediate repositioning to avoid dropping or damaging the payload. The crew on deck communicated continuously, calibrating adjustments against live sonar and visual feedback to maintain control. Each small success was measured against the unpredictable environment, emphasizing the fragile balance between human intervention and oceanic forces. Displaced sediment traced a tentative path leading away from the hull, and fragments of protective casing suggested that part of the cargo had been disturbed by forces still invisible to the crew. Tiny particles swirled in eddies, forming faint trails that hinted at movement over hours or days. Small shards of polymer and metal indicated localized abrasion or minor impacts, yet the overall pattern was inconsistent with normal deployment or handling. The scattered fragments created a subtle puzzle, a hint that something beyond ordinary currents had influenced the container's positions, leaving investigators with more questions than answers. Engineers and scientists debated whether sudden sub-bottom slides, strong lateral currents, or entanglement with previously unmapped debris had contributed, recalling incidents from other Ligurian shelf expeditions. Historical records noted rare but significant turbidity flows in the region, capable of moving sediments and small equipment across several meters. At the same time, the narrow canyons and steep gradients could amplify even minor surges, creating unexpected force vectors. Yet the combination of observed disturbances and environmental data did not fully explain the apparent disappearance or shifting of some of the containers. Every hypothesis addressed part of the evidence, but none could account for the complete pattern. Extended surveys broadened the search, mapping canyon gradients and unseen ridges that could funnel water and debris unpredictably, yet offered no direct evidence of the missing containers. Multi-beam sonar sweeps and ROV transects recorded the contours of the seabed, revealing hidden depressions and narrow gullies that could conceal objects from both visual and acoustic detection. Some areas showed minor sediment slides or scoured channels, suggesting that localized flows had occurred, yet the exact mechanism by which the containers had been displaced remained uncertain. These additional observations offered context, but did not resolve the central mystery of the silent hall. Recovered fragments, including severed tether lines and damaged sensor housings, provided only partial clues, each piece raising more questions about the silent forces at work. Structural examinations of the fragments revealed clean breaks and abrasion patterns consistent with both mechanical stress and the unpredictable flow of dense water along the shelf. Electrical and data connections were partially corroded but not failed by prolonged exposure, suggesting a sudden event rather than slow degradation. The fragments hinted at the sequence of disturbance, yet they lacked sufficient information to reconstruct the full story. Meticulous documentation of currents, ROV operations, and sonar observations failed to reveal the hall's final disposition, leaving the expedition's outcome unresolved. Reports documented every displacement, current reading, and sediment plume. Yet even the most detailed reconstructions could not account for the complete disappearance or relocation of the containers. The Pelos shelf, with its hidden canyons and shifting flows, had preserved its secrets, leaving investigators with an incomplete understanding of the forces that had acted on the silent hall. Buried among the labyrinthine canyons, the vanished containers remained, their stories swallowed by shadow and silent depths. The downed drone beneath the Wedel gyre. The Wedel gyre churned far below the vessel Antarctic horizon, where a remotely operated drone prepared to descend toward uncharted seafloor beneath drifting ice shelves. The mission aimed to map sediment composition, survey subglacial meltwater channels, and record microfauna activity in a sector largely untouched by human exploration. Equipped with high-resolution cameras, sediment samplers, and pressure-tolerant instruments, the drone represented the cutting edge of polar oceanography. Its deployment was considered routine, yet the gyre's immense circulation and the shifting ice above added an element of unpredictability that scientists and engineers could not fully anticipate. Dense, near-freezing waters swirled around the drone's trajectory, carrying brine-enriched layers that shifted unpredictably with the gyre's cyclonic currents. Temperatures hovered just below the freezing point of freshwater, while salinity gradients created density-driven layers that altered the drone's buoyancy. Current measurements recorded subtle vertical and lateral flows, suggesting the presence of under-ice channels capable of redirecting water at speeds exceeding 1 meter per second. Even minor miscalculations in thruster output could result in unintended drifts, forcing operators to constantly adjust navigation to compensate for both predictable and hidden flows. Early sonar readings revealed a seafloor of fractured ice scours, sediment ridges, and occasional drop-offs, punctuated by pockets of suspended particulates stirred by hidden flows. These features indicated a landscape shaped by centuries of glacial advance and retreat, punctuated by localized erosion from sub-ice meltwater outflows. Scattered rocks and compacted sediment formed ridges that could trap debris or divert instruments, while soft silt and isolated depressions concealed depressions that were difficult to map precisely. The combination of complex terrain and dynamic water movements demanded careful monitoring, with every meter logged for both safety and scientific accuracy. Sudden spikes in pressure and erratic positional data signaled the first anomaly, an unexpected disturbance that challenged the drone's navigational algorithms. Depth sensors recorded abrupt fluctuations inconsistent with steady descent, while inertial measurement units reported slight tilts beyond program tolerances. These readings coincided with brief interference in acoustic communications, suggesting that environmental conditions, rather than immediate mechanical failure, were influencing the drone's stability. Crew members studied the logs, aware that even minor anomalies at such depths could escalate into complete system compromise. Operators adjusted thrusters and recalibrated sensors, attempting to regain stability while ice-reflected light and turbulent eddies complicated visual guidance. Each adjustment required balancing counter-thrust against the unpredictable lateral flows created by the gyre's sub-ice currents. Suspended particulates reduced camera clarity, producing shifting patterns that gave the illusion of movement unrelated to the drone's actual path. The team executed iterative corrections, relying on both sonar interpretation and visual feedback, yet the underlying forces at work remained elusive, resisting precise quantification. Environmental analysis suggested sub-ice channels and brine jets could generate localized currents strong enough to push the drone off course, yet the exact forces remained uncertain. Studies of previous Wedel gyre expeditions indicated that dense saline outflows can create narrow, fast-moving streams near the seafloor, capable of displacing small autonomous vehicles or sampling instruments. Ice-kill formations further amplified turbulence, generating unexpected vortices and eddies. Even with high-resolution mapping of the area, these dynamic features remained difficult to anticipate, leaving the drone vulnerable to sudden deviations from its intended trajectory. Engineers scrutinized structural logs and internal diagnostics for signs of mechanical failure, cold-induced brittleness, or sensor misalignment under extreme Antarctic pressure. The drone's titanium-reinforced hull and pressure-rated housings were designed to withstand depths exceeding 2,000 meters, yet prolonged exposure to sub-zero temperatures and abrupt current changes could stress components in subtle ways. No pre-deployment anomalies had been detected, and systems had functioned normally during surface checks. Nonetheless, the extreme environment introduced variables that could manifest only during active operations, leaving the team to consider both natural and technical explanations in tandem. Acoustic sweeps and partial telemetry retrieval provided fragments of the drone's path, hinting at sudden vertical movement and lateral drift inconsistent with planned descent patterns. Sensor data indicated brief accelerations and decelerations, as though the drone had been caught in a hidden current funnel or momentarily trapped against an unseen obstruction. Gaps in recorded data prevented a continuous reconstruction, and small inconsistencies suggested that portions of the descent may have occurred in regions where signal propagation was impeded by ice formations or density layers. Each recovered fragment of information provided clues, but never the full picture. Team discussions weighed mechanical failure against environmental interference, comparing previous Wedel deployments where drones had survived similar currents without incident. Historical records noted that even minor sub-ice turbulence can produce unexpected pressure pulses, yet earlier missions had never produced the abrupt and complete loss observed here. Hypotheses ranged from brief encounters with under-ice jets to sudden entrapment in sediment-laden depressions, but each scenario left unanswered questions about the drone's final location. The combination of extreme cold, dense water layers and complex terrain created conditions unlike any other polar deployment. Even with meticulous reconstruction, the sequence of events leading to the drone's abrupt disappearance could only be partially inferred, leaving investigators with persistent uncertainty about the forces at play. Sonar maps, partial telemetry, and recovered sensor logs offered glimpses into the dynamic interplay between the drone and its environment, yet the full story remained out of reach. The Wedel gyre, vast and largely unobserved, had claimed both instrument and data, leaving scientists with fragments of a mission whose conclusion defied reconstruction. Suspended within the gyre's swirling layers, the downed drone waits, swallowed by currents that erase its tail in the frozen deep. The lost archive under the Japan Trench. Beneath the towering waves of the Northwest Pacific, the research vessel Kaijin Maru prepared to recover a long-lost archive that had slipped beneath the Japan Trench years earlier, its precise contents and location uncertain. The archive, deployed as part of a deep ocean monitoring program, contained pressure-resistant instruments, recorded environmental data, and sensitive research modules intended to study tectonic activity along the subduction zone. Its disappearance had gone unnoticed for some time, only coming to attention when a planned survey revealed gaps in long-term data. The team assembled for the recovery understood that the trench's extreme environment would push both submersible technology and human oversight to their limits. Descending into near-total darkness, the submersible navigated through crushing pressures exceeding 1,000 atmospheres, where temperatures hovered just above freezing and tectonic forces subtly flexed the surrounding seafloor. The Japan Trench, part of the convergent boundary where the Pacific Plate subducts beneath the Okhotsk microplate, presented one of the most inhospitable regions on Earth. Deep currents, influenced by the subduction slope and trench topography, created unpredictable water movement that could destabilize even well-calibrated instruments. Sensors monitored for minute variations in pressure and depth, providing critical information for the team as the submersible approached depths nearing 10,800 meters. Sonar revealed a rugged trench floor littered with sediment ripples, scarred rock faces, and scattered debris, creating a labyrinthine landscape that obscured the archive's resting place. Dark shadows stretched along steep escarpments, while isolated mounds of compacted sediment hinted at localized shifts in the seafloor. Occasional outcrops of basalt and chert punctuated the otherwise uniform slope, forming natural barriers that could conceal objects from visual or acoustic detection. Navigating this terrain required constant adjustment, as even small inclines could deflect the submersible's path, making precise localization of the archive a complex task. Unexpected turbidity currents swept past the submersible, stirring sediment and creating fleeting clouds that momentarily obscured visual feeds and distorted depth measurements. These currents, generated by minor slumps along the trench wall, carried fine particulate matter that interfered with sonar reflections and camera clarity. Observing their movement revealed the strength and direction of sub-trench flows, yet each cloud introduced a margin of error in calculating the archive's position. Operators documented each disturbance, aware that the trench itself might actively conspire against their efforts to recover the modules. Manipulator arms extended cautiously, testing the archive's position, while onboard engineers monitored structural integrity and pressure tolerances with every centimetre of movement. The archive's casing had been engineered to withstand immense pressure, but decades of exposure to trench conditions, including microseismic activity, sediment loading, and salt infiltration, raised questions about its current stability. Gentle probing revealed minor shifts in position, suggesting that the modules had partially settled into soft sediment or been nudged by subtle tectonic movements. Each successful grasp was balanced against the risk of destabilizing the surrounding trench floor, emphasizing the precarious nature of the operation. Geological activity suggested that subduction tremors and minor slumps could have shifted the archive from its original coordinates, leaving investigators to contend with both natural and mechanical uncertainty. Historical seismic records indicated frequent low-magnitude tremors along the trench slope, capable of displacing loose sediment and small objects. These movements, though invisible from the surface, could subtly alter the position of equipment and create uneven sediment drifts that interfered with recovery. The team considered whether such shifts had contributed to the archive's current concealment, compounding the mystery surrounding its disappearance. Fragments of casing and partial log recordings were recovered, offering tantalizing clues about the archive's contents and its final descent into the trench's inky depths. Shards of titanium and pressure-resistant polymer bore evidence of abrasion against rock faces, while intermittent data suggested periods of uninterrupted operation before sudden signal loss. These remnants provided a partial timeline of the archive's fate, yet they revealed little about the precise environmental conditions that may have caused its partial burial or displacement. Each fragment became a critical puzzle piece, hinting at forces and events that the submersible could only observe indirectly. Analysts compared environmental readings with engineering data, weighing the influence of sediment flows, tectonic shifts, and pressure anomalies on the archive's disappearance. Cross-referencing sonar maps with sensor logs allowed investigators to trace potential paths the modules may have taken as they settled into the trench floor. Despite the level of precision achievable, inconsistencies persisted in the data, leaving small but crucial gaps that prevented a full reconstruction. The combination of extreme depth, shifting sediment, and tectonic instability created conditions that both enabled and obscured the archive's final resting place. Historical expeditions to the Japan Trench recorded similar losses, where instruments and research modules vanished under extreme conditions, hinting at a persistent pattern of deep-sea disappearance. Submersibles and freefall probes had occasionally failed to recover deployed equipment, leaving only partial data to be interpreted long after missions concluded. These accounts framed the current expedition within a broader context of trench-related mystery, emphasizing that the deepest reaches of the Pacific remain largely inaccessible and unpredictable despite decades of technological advancement. Even after exhaustive mapping and repeated dives, the archive's complete recovery remained elusive, leaving the trench's secrets intact beneath layers of sediment and shadowed rock. The team could only speculate on the precise forces that had contributed to its concealment, balancing scientific observation with the recognition that some elements of the deep ocean resist full understanding. Every piece of recovered evidence deepened the sense of intrigue, highlighting both human ingenuity and the enduring power of one of the planet's most extreme environments. Concealed within the crushing depths of the Japan Trench, the lost archive waits, beyond the reach of time or human discovery. The corroded sphere of the Kadic Gap. During a deep ocean survey of the Kadic Gap, the submersible Nereid explorer detected an unusual metallic object partially buried in sediment, its surface etched with intricate corrosion patterns. The discovery was unexpected, as the expedition had been focused on mapping hydrothermal vents and documenting sediment flows along this narrow section of the trench. Initial sonar readings indicated a compact, spherical form, while visual inspections hinted at a deliberate geometry inconsistent with natural rock formations. Researchers speculated that the object had remained undisturbed for decades, shielded by sediment and the trench's extreme environment, waiting to reveal both its composition and its origin. As the vessel descended towards 6,000 meters, hydrothermal currents swirled unpredictably through the narrow trench corridor, carrying heated water and mineral particulates that affected both navigation and instrumentation. These currents, influenced by the active subduction zone and nearby volcanic structures, produced localized turbulence capable of destabilizing submersibles. Temperature gradients fluctuated sharply over short distances, while mineral-rich plumes intermittently obscured optical sensors. The team relied on real-time adjustments and precise thruster modulation to maintain proximity to the object without disturbing the surrounding sediment, aware that even minor miscalculations could compromise observation. The sphere appeared almost perfectly round, yet closer inspection revealed irregular pitting, encrusted microbial colonies, and faint traces of oxidized metals that hinted at prolonged exposure to the extreme environment. Biofilms clung to its surface, suggesting chemical interactions between metal and seawater had encouraged microbial growth in a manner similar to deep-sea hydrothermal deposits. Pitting and corrosion were uneven, indicating differential exposure to currents and sediment abrasion. The visual evidence implied both a long submersion and ongoing chemical transformation, creating a complex profile for scientists to interpret. Local temperature readings fluctuated sharply, suggesting intermittent venting from nearby fissures, while subtle chemical anomalies hinted at ongoing interactions between the sphere and its surrounding seawater. Measurements of pH and dissolved metals suggested localized mineral enrichment, likely sourced from hydrothermal activity along the trench wall. These anomalies created subtle currents and density differences in the immediate water column, producing variations that could influence the object's position over time. Understanding this interaction became essential, as even small environmental factors might explain the sphere's corrosion patterns and partial burial in sediment. Manipulator arms extended carefully to measure the object's diameter and surface composition, recording resistance and tactile feedback as engineers attempted to determine density without dislodging it from the sediment. Instruments probed the metal, taking samples for chemical and isotopic analysis, while sensors logged strain and pressure. The sphere's metallic composition remained elusive, with preliminary spectroscopy indicating a complex alloy potentially resistant to rapid corrosion, yet exhibiting unique surface transformations under deep-sea conditions. The precision required for these assessments underscored the difficulties of handling objects at extreme depths, where the margin for error was measured in millimeters. Fine-grained volcanic ash and compacted silt surrounded the sphere, and pressure calculations indicated that even slight movements could trigger microslides that would bury it further or roll it into a depression. Sediment cores revealed layers of deposition corresponding to regional seismic activity, suggesting that episodic tremors had contributed to partial coverage over time. The submersible's presence and any attempted manipulation risked destabilizing these layers, emphasizing the delicate balance between exploration and preservation. Observers noted that the trench's morphology, steep walls and sediment terraces, amplified the consequences of even minor disturbances. Researchers debated possible origins, considering whether the sphere was a relic of human exploration, a natural concretion formed under hydrothermal influence, or an artifact of unknown provenance entirely. Its uniform roundness and metallic construction suggested intentional fabrication, yet no records or missions aligned with the object's location. Natural formation under hydrothermal processes seemed unlikely due to the precise geometry, while alternative theories of unknown origin remained speculative. Each possibility offered partial explanations, yet none fully accounted for the combination of corrosion, microbial colonization, and environmental embedding observed. High-resolution imaging and limited sample collection provided chemical and microbial data, offering fragments of understanding while leaving the majority of its history concealed beneath mineral layers. Spectroscopic analysis indicated complex oxides and sulfides formed over decades, while microbial mats were found to accelerate localized corrosion. Imaging captured minute surface details, revealing microfractures and sediment inclusions that hinted at episodic burial and exposure. Despite this wealth of data, the sphere's complete narrative remained elusive, with each fragment deepening both scientific insight and mystery. Comparisons with other deep-sea spheres recovered from abyssal plains and trench gaps highlighted the Kadic object's unusual resilience to corrosion and its unique placement amid active tectonic forces. Previous finds often exhibited heavy deformation or sedimentary entombment, yet this sphere maintained structural integrity while displaying highly localized corrosion. Its survival in an area subject to hydrothermal currents, minor earthquakes, and shifting sediment underscored both its robustness and the dynamic conditions of the Kadic Gap. These contrasts reinforced the object's exceptional nature and the difficulty of categorizing it within known patterns. Repeated scrutiny and careful logging failed to alter the sphere's isolation, highlighting the ocean's capacity for concealment and preservation. Even with advanced technology, the teams could only gather partial information, forced to reconcile empirical data with enduring uncertainty. Every measurement and visual capture offered insights, yet the sphere retained an aura of mystery, emblematic of the deep-sea environment that continually conceals more than it reveals. Encased in the currents and sediment of the Kadic Gap, the corroded sphere remains, quietly preserving a history beyond human reach. The lamps of the Caribbean escarpment. Faint points of illumination appeared unexpectedly on the ROV's monitors, scattered across the steep slope of the Caribbean escarpment in patterns that resisted immediate explanation. The expedition team aboard the Nereus Explorer had initially been focused on mapping fault scarps and sediment flows near the escarpment's edge, but these glowing anomalies diverted attention and introduced a sense of both wonder and uncertainty. Sonar readings suggested that the sources were located on protrusions or minor terraces along the slope, yet no large geological features corresponded with their positions. Even at first glance, the lights seemed deliberate, their distribution resisting simple natural explanation while remaining entirely within reach of the ROV's sensors. Currents funneled along the escarpment created subtle turbulence, carrying fine volcanic silt and influencing the movement of particulate matter around the glowing formations. These currents, driven by the Caribbean plate's slope toward the Puerto Rico Trench, were capable of shifting sediment and altering visibility within meters of the ROV. Mineral-rich plumes occasionally clouded the camera feeds, their swirling patterns producing a ghostly effect around the lights. The expedition team noted that even small variations in water density could refract the glow, giving it an otherworldly shimmer that complicated accurate observation. Closer inspection revealed that each luminous point varied slightly in hue, some emitting a cool blue glow while others shimmered with a muted green, and their intensity pulsed with irregular rhythms. The team adjusted light sensors to quantify these variations, noting that some flashes lasted mere seconds while others lingered in soft pulses that seemed synchronized with no discernible environmental trigger. Occasional flickers coincided with passing sediment or microcurrents, but many luminescent bursts appeared entirely independent, giving the appearance of autonomous activity across the slope. It was considered that the glowing lights might originate from colonies of bioluminescent organisms along fissures, or from minerals reflecting chemical plumes in the surrounding water. Hydrothermal vents and fissures along the escarpment occasionally produce luminescent chemical reactions or deposit minerals that catch ambient light, yet none of the known formations in this region were reported to generate steady, localized glows of such variety. Observations suggested that either the phenomenon was rare, previously undocumented, or involved a combination of factors not fully understood, leaving a persistent tension between natural explanation and anomaly. High-sensitivity photometers and multi-angle cameras recorded the light's spectra, while sonar mapping confirmed that their positions did not correspond with any detectable geological protrusions or artificial debris. Spectral analysis revealed wavelengths consistent with deep-sea bioluminescence in some instances, yet others fell outside typical biological emission ranges. The ROV captured microscopic images of fine sediment surrounding the glowing points, showing evidence of intermittent movement and disturbance. But no organism could be conclusively linked to the light sources. The combination of measurements suggested a hybrid phenomenon, at the intersection of biology, mineralogy, and perhaps an unknown factor altogether. Sediment shifts and microcurrents altered the apparent placement and orientation of several lamps, making it difficult to determine whether they were stationary or subtly drifting along the slope. Even slight adjustments of the ROV thrusters caused the surrounding silt to cloud, temporarily masking individual lights. Observers speculated that some of the glows might be anchored to small fissures or outcroppings, while others appeared suspended, hinting at structures or organisms able to maintain position against the prevailing currents. The interplay of flow, particulate matter, and luminescence created an environment that was both mesmerizing and confounding. A debate arose among the team as some argued for a natural origin rooted in vent chemistry, while others noted anomalies in regularity and distribution that suggested a deliberate placement. Certain lamps seemed evenly spaced along minor ridges, a pattern that defied the randomness expected of purely biological colonies. Conversely, the irregular pulsing of individual lights resembled behaviours found in deep-sea organisms. Reconciling these contradictions became the primary challenge, with each hypothesis accounting for part of the phenomenon while leaving other aspects unexplained. Over the course of repeated dives, the light's behaviour seemed to change, with some diminishing entirely and others flickering intermittently, accompanied by the quiet passage of deep-sea fauna. Small crustaceans and polychaete worms were observed moving through the illuminated zones, their silhouettes momentarily accentuating the glow. Researchers noted that light intensity fluctuated independently of current velocity or sediment displacement, hinting at mechanisms operating beneath the slope or within structures hidden from direct view. The changing luminescence added a temporal dimension to the mystery, suggesting that the lamps were not static phenomena but dynamic entities. Comparable phenomena in other trench-adjacent escarpments had been attributed to biological colonies or mineral reflections, yet the Caribbean lamp's combination of regularity, hue variation, and positional stability remained unmatched. Investigators referenced prior deep-sea studies from the Puerto Rico Trench and the Cayman Trough, where glowing microbial mats or vent minerals had been documented, but none exhibited the coordinated presence or persistent visibility of the escarpment lamps. This discrepancy reinforced the impression that the lights represented a singular and enigmatic occurrence, defying easy categorization. Though every observation was recorded, the source of the glowing formations remained mysterious, yielding data that challenged the limits of current understanding. High-resolution video, sediment samples, and spectral readings provided material for analysis, yet each answer seemed to uncover additional uncertainties. The lights retained an eerie autonomy, a subtle reminder that the deep ocean can harbour phenomena that elude even the most sophisticated human exploration. The Caribbean escarpment's darkness is punctuated by lamps that pulse and fade, as if the deep itself were deliberately shielding its truths. The fallen tower of the Azors plateau. A massive vertical form emerged on the ROV's sonar display, its sheer height dominating the surrounding seafloor and drawing immediate attention from the Azors plateau expedition team. The vessel Abyss Explorer had been conducting a routine mapping survey of the plateau, a region characterized by transitional depths between the mid-Atlantic ridge and the Azores archipelago, when the anomaly appeared. At first glance, the tower's presence seemed improbable. A structure rising from a relatively flat sediment plain, its sides nearly perpendicular and sharply defined. The team noted the sense of scale immediately, estimating a height of nearly 90 meters, with a width that extended across a modest terrace suggesting both stability and an enduring presence through tectonic and sedimentary activity. The tower rose with an imposing regularity, its sides steep and mostly uninterrupted, tapering slightly toward a fractured summit that hinted at violent geological forces. Cracks and minor spalling along the uppermost section suggested episodes of collapse or intense pressure over a millennia, yet the vertical orientation had persisted, defying the surrounding currents that might have otherwise eroded a more conventional formation. Shadows from the ROV's light stretched across the walls, accentuating subtle ridges and indentations, while sediment cascades at the base hinted at ongoing slow-moving processes shaping the tower over time. Encircling the structure, basaltic pillow flows and sediment terraces revealed a history of tectonic activity and volcanic deposition, providing a natural framework that both explained and complicated the tower's presence. The plateau itself was a product of repeated eruptions, faulting and uplift along the mid-Atlantic ridge, yet nothing in prior surveys had indicated a formation of this magnitude or geometry. Sediment layers accumulated unevenly around the tower, suggesting intermittent landslides or slumping events, while nearby hydrothermal vent fields contributed mineral deposits that sometimes adhered to the vertical faces. Upon closer visual inspection, subtle straight edges and near-symmetrical fractures suggested an organization that could not be entirely attributed to typical basaltic cooling patterns. Some of the walls exhibited faintly parallel fissures, resembling jointing in columnar basalts, yet far more pronounced in their consistency and orientation. The summit, jagged and uneven, bore small overhangs that defied simple erosional explanations, prompting speculation that forces beyond ordinary volcanism or tectonics might have influenced its shape. ROV instruments mapped the tower's faces in high resolution, while sediment cores and rock samples were extracted to determine mineral composition and assess potential artificial influence. The data confirmed a primarily basaltic composition, yet variations in crystallization and trace minerals within fractures indicated differential cooling or hydrothermal alteration. Scientists recorded minute differences in density along the tower's walls, suggesting localized heating events or chemical deposition, and meticulously logged each anomaly for comparison with known geological benchmarks. Strong currents at mid-depth swept across the vertical faces, stirring sediment and occasionally exposing fissures that might otherwise have remained hidden, while minor tremors caused visible shifts in fractured sections. The combination of current-induced movement and tectonic tremors created a dynamic environment, one in which previously concealed fractures could suddenly reveal themselves. Observers noted that some debris at the base appeared freshly displaced, raising questions about the stability of the structure and the frequency of its minor collapses. Discussion within the team grew heated, with geologists advocating for natural volcanic pillars, while others considered tectonic uplift or an origin yet unexplained by current knowledge. Comparisons to mid-ocean ridge seamounts, rift-aligned columns and basaltic dikes provided partial analogues but failed to explain the tower's singular verticality, its isolated placement, or the regularity of its fractures. Some suggested that the combination of uplift, minor collapse, and hydrothermal deposition could mimic an intentional structure, yet no concrete evidence supported deliberate construction. Over successive dives, the tower's fractured summit revealed subtle movements, sediment displacement along its sides, and interactions with small benthic creatures navigating the vertical landscape. Crustaceans, polychaete worms, and occasional echinoderms were observed moving across ledges and crevices, highlighting the tower as both a geological and ecological feature. Slight rockfall from the summit occasionally triggered cascading silt clouds, temporarily obscuring lower sections and providing fleeting glimpses of underlying formations. The interplay of movement, sediment and life added a sense of temporal fluidity to a structure that otherwise seemed eternal and immovable. Structures of this kind exist elsewhere on oceanic plateaus and rift zones, but the unique combination of scale, regularity and isolation marked this segment of the Azors plateau. Columnar basalts along rift zones can reach impressive heights, but they often occur in clusters or along fissure swells rather than as a solitary tower standing sharply against a sedimented plain. The Azors structure's combination of dimensions, symmetry and persistent presence suggested a rare geological circumstance, one not easily replicated in other known oceanic terrains. The fallen tower resisted every attempt at classification, and thorough documentation revealed only further mysteries for the expedition. Each dive, each sample, and each mapping pass produced additional data, yet none could fully account for the tower's height, shape, or fracture patterns. Even the most plausible geological explanations were shadowed by lingering uncertainty, reinforcing the notion that the ocean's depths often harbour phenomena beyond current comprehension. Above the plateau's muted expanse, the fallen tower persists as a silent sentinel, its origin and purpose locked in the shadows of the deep ocean. The sounding of the Mozambique corridor. On the early morning horizon, the RV Indus traced a path over the restless waters of the Mozambique Channel, the expedition team scanning charts for a subtle trench that had long eluded detailed study. Though the surface appeared calm, the depths below were a complex labyrinth of ridges, sediment flows, and tectonic scars. The corridor they sought was a shadowed feature on historic maps, barely perceptible except through careful interpretation. As the vessel slowed and instruments were deployed, crew members exchanged glances at the faint lines appearing on the preliminary maps, their shapes promising months of careful exploration and analysis. Even as the sun rose over the Indian Ocean, the corridor seemed to stretch endlessly, a linear scar hinting at forces the team had yet to understand. The corridor soon revealed itself as a narrow, sharply defined swath running across the abyssal plain, its straightness and uniform slopes hinting at forces beyond ordinary sedimentation. The sides rose gently but consistently, forming terraces that gave the impression of deliberate engineering rather than chaotic natural processes. Shadows cast by the vessel's lights occasionally exposed small depressions along the walls, each shadow morphing as currents swept the fine sediment, creating a shifting mosaic of light and dark. Even from the surface, its striking linearity was impossible to ignore, and the team began to speculate whether similar corridors might exist undetected elsewhere in the Indian Ocean. Subtle irregularities beneath the seabed were detected in early acoustic measurements, forming patterns that could not be readily explained. Periodic reflections suggested hidden ridges or undulations in the channel floor, their precise spacing hinting at forces acting over long time scales. Occasionally, echoes appeared in unexpected locations, vanishing entirely in the next sweep, a ghostly signature that unsettled even the most experienced geologists aboard. The data were methodically logged, each anomaly catalogued with time, depth and sweep angle, forming a record of a structure that seemed almost alive in its subtle variations. Surrounding ridges, minor volcanic outcrops and tectonic faults painted a complex regional picture, yet none accounted for the corridor's remarkable linearity or precise gradients. The Mozambique Channel is tectonically active, shaped by the separation of the Somali and Nubian plates and influenced by nearby mid-ocean ridges. Fault scarps cut across the seabed in irregular patterns, pillow lavas bulged unpredictably, and sediment flows shifted over centuries, but none exhibited the uniform alignment or the long, narrow trajectory of this corridor. It seemed almost anomalously orderly within an otherwise chaotic abyssal environment. Multi-beam mapping and sub-bottom profiling exposed subtle depressions and ridges along the corridor floor, some appearing so regular they seemed almost deliberate in their placement. Alternating shallow terraces and elongated troughs created a rhythm along the channel, as if the ocean floor itself were following a hidden blueprint. Core samples taken from these features revealed layers of clay, silt and fine sand, occasionally interrupted by coarser deposits indicative of episodic turbidity currents. Even small features only a few meters across were repeated in sequence, producing a pattern the team could not immediately reconcile with conventional sediment transport or tectonic activity. Currents sweeping through the channel stirred fine sediments, occasionally exposing terraces and fissures that offered fleeting glimpses of the formation's inner structure. Small benthic creatures, brittle stars, shrimp, and polychaetes clung to slopes and terraces, their presence highlighting how life had adapted to the subtle stability of the channel. On several occasions, sediment clouds obscured ROV lights entirely, revealing a silent world in motion, where even the smallest disturbance reshaped shadows and forms. These fleeting glimpses reminded the team that the corridor, though linear and seemingly permanent, was dynamic in ways that only deep-sea observation could reveal. Disagreements arose among researchers. Some pointed to rift-driven formation or sediment flow, while others speculated on a structural process beyond current understanding. The linearity suggested guidance by tectonic forces, yet the internal terraces and subtle ridges implied deposition or erosion occurring in repeated cycles. A few scientists even speculated on influences so slow and invisible that they left almost no surface evidence: current subduction-driven compaction or deep-sea hydraulics capable of carving shapes over eons. Every new dataset seemed to confirm part of one theory while complicating another, leaving the team in a state of cautious fascination. Multiple survey passes captured shifting acoustic signatures, minor sediment slumps, and subtle anomalies, suggesting a dynamic corridor that resisted static description. Tiny echoes would appear and vanish. Terraces seemed to deepen slightly under the pressure of currents, and occasional collapses revealed fine layers that might have taken centuries to accumulate. The ROV navigated carefully along the channel, tracing each curve and slope while the crew compared readings with historical charts, seeking precedent in previously surveyed submarine canyons or rift-aligned troughs. Each comparison emphasized the corridor's singularity, a formation distinct from known oceanic features. Other deep-sea channels fell short in comparison, lacking the Mozambique corridor's unusual combination of linearity, terraces, and subtle depth anomalies. While submarine canyons on continental margins often displayed dramatic erosive patterns and mid-ocean rift troughs exhibited chaotic faulting, no other feature matched the combination of linearity, faintly regular internal topography, and persistent acoustic oddities. The corridor seemed almost like a hidden fingerprint left by a force no human yet fully understood, a trace of slow, patient activity written in sediment and stone. Extensive scrutiny revealed little. The corridor's purpose and origin continued to confound geological expectations. Every dive, core sample, and acoustic pass added pieces to the puzzle, yet the full picture eluded comprehension. Scientists aboard the RV Indus could chart terraces, map ridges, and measure slopes, but the subtle symmetry and long-scale linearity of the corridor hinted at processes beyond ordinary tectonic or sedimentary activity. Even within the quiet, sweeping currents of the Mozambique corridor, the ocean keeps its hidden geometries, leaving their origin and meaning beyond human reach. The Riftlander of the Drake Passage. The salvage vessel drifted slowly on the dark swell above the turbulent waters of the Drake Passage, the crew uneasy under a low grey sky as the recovery team prepared to raise the malfunctioning Rift Monitor lander from the ocean floor. That underwater device, lowered weeks earlier to record tectonic strain at a submerged rift where the Antarctic and South American plates converge, had ceased transmitting normal data days ago and instead emitted a long metallic call that scrambled onboard systems and silenced routine distress pings. The mission's objective had been straightforward: retrieve the lander for diagnostic analysis and redeploy a fresh unit. Instead, the expedition devolved into something neither charts nor logic could explain. Drake Passage was notorious among deep-sea mariners for its savage currents, swirling eddies, and unpredictable storms. Its known depths beneath the survey grid ranged between 3,300 and 4,200 meters, where water temperature rarely rose above 1.5 degrees Celsius, and pressure crushed anything not designed to endure the deep. The convergence of the Antarctic circumpolar current with powerful southern gales made surface conditions especially treacherous, yet the fleet had weathered similar storms before. The team believed this descent and recovery could be done within a narrow window of calm seas and manageable drift. But the moment they engaged the winch cables, the sea seemed to conspire against them. The Rift Monitor lander itself had been built with robust titanium cladding, sensor arms extending outward like mechanical ribs, and automated acoustic modems to transmit strain gauge readings once tethered. It housed seismic sensors, pressure gauges, and temperature probes, all engineered to trace minute movements in the ocean floor where tectonic plates sheared past each other. Its descent had been uneventful, touching down gently amid soft silt stirred only by distant currents. For days it yielded quiet, almost hauntingly regular logs. Then, without warning, data streams ceased, and the audio channel erupted in a cold, resonant ping, like metal scraping on metal, followed by a sustained vibration that shook the modem until it finally died. The moment the recovery team initiated the lift, the lander's exterior shuddered despite the absence of visible current or collision. The winch line strained under the weight that fluctuated by the second. Instruments aboard the support vessel registered wide swings in load, too erratic to ascribe to a snag in the tether. The crew observed no snag on sonar, nothing protruding from the seabed's map. Still, the cable jumped, twisted, then slackened, only to jerk again as if something alive fought against being raised. After hours of tense deliberation, the salvage commander ordered the descent of a pair of deep-sea divers in atmospheric suits, along with a remotely operated vehicle to attach additional harnesses. The weather held grudgingly calm, sea charts promised no hazards near the recovery site, and on paper, nothing should have gone wrong. The call from the lander had ended minutes earlier, a final shriek of tortured metal, leaving only silence on the hydrophones. But keen ears on deck reported that faint reverberation lingered beneath the waves, a low dronescape that made the steel hull of the mothership groan and small unsecured tools rattle in their trays. At 3,500 meters down, the first diver's floodlight cut through cold blackness. The seabed lay flat and featureless, save for the lander, a hulking silhouette bathed in the pale glow of spotlights. Faint currents tugged at the harness cords. As the diver clipped a clasp to the lander's recovery ring, the sonar feed aboard the support vessel crackled unexpectedly. The return signal showed a second shape adjacent to the lander, identical in outline but shifted slightly, as if a phantom copy of the lander hovered just beyond visibility. The ROV's lights scanned the zone. Nothing. The diver panned upward, but the cameras revealed only the distant glow of the lander's lights beating softly through the darkness. Suddenly, the suit's orientation instrument spun wildly. The diver's voice, transmitted through comms, cut off mid-sentence. On the surface, the winch operator felt the cable slacken, then tighten, then loosen again. The sonar dome registered an agonized ping from the suit's transponder. A single burst that extinguished almost as swiftly as it appeared. Attempts to reel in the cable met only snagged resistance, friction, and then cold emptiness. The second diver and the ROV were ordered to abort. The cables reeled in, empty. What had been attached to the lander no longer remained. In the hours that followed, the support vessel circled the area, deploying side-scan sonar and magnetic anomaly detectors. They located a twisted hunk of metal 30 meters from the lander's expected location, or what remained of one of the diver's tether clamps. No bodies, no sign of life, only the fractured hardware yawing gently above a featureless seabed. The lander itself lay where they had first seen it, untouched and silent, as though the divers had never existed. An official report filed by the expedition simply states loss of contact with dive team. The entry notes that all retrieval equipment sustained irreparable damage, and the site continues to register anomalous acoustic reflections at irregular intervals, often late at night, according to watch logs. No further salvage attempts were authorized. The ocean there was declared unsafe for future operations. The Rift Monitor remains on the seabed, a silent witness to some unknown force. The fate of the divers is marked as presumed lost, bodies and remains never recovered. Today, decades later, tales from mariners claim that passing ships sometimes catch strange echoes on sonar as they sail near the wreck's coordinates, hearing a metallic cry that does not quite belong to any known vessel. Oceanographers speculate about malfunctioning instruments, deep-sea landslides, or tectonic shifts, but none offer a satisfying explanation. The black waters of Drake Passage earned a new reputation, no longer simply violent and cold, but unnerving in their capacity to swallow machines and men alike in absolute silence. The lander's signals were met with a presence from the deep, which rose briefly before disappearing into the shadowed currents. the copper wreck near the Bonan chain. The morning haze over the Bonan Islands revealed the faint silhouette of the RV Cayenne, poised above waters long whispered about in maritime lore. The vessel's crew prepared instruments and logged coordinates, aware that these stretches of ocean had long concealed wrecks whose stories had been swallowed by currents and centuries of saltwater corrosion. The expedition, commissioned to investigate a vessel rumoured to carry significant quantities of copper and other metals, followed historical accounts and scattered sonar readings that suggested a remnant lying far from any navigational chart. Even as sunlight fractured across the gentle swell, the crew sensed that the discovery below might not fully align with recorded history, a subtle tension hanging over the deck as the submersible prepared for deployment. Shifting sediments and jagged undersea peaks traced the path toward the site, the deep currents adding layers of complication to navigation. Charts of the Bonan chain revealed volcanic remnants, slopes scarred by ancient landslides, and troughs carved by tectonic movement, each feature complicating sonar readings and ROV maneuvering. Currents occasionally shifted sediment in unpredictable ways, creating ephemeral ridges and valleys across the abyssal plain. This was a region where even small miscalculations in depth or angle could result in lost instruments, and the team maintained a careful rhythm of observation, calibration, and adjustment to ensure the submersible's safety. Lights from the submersible pierced the gloom as it descended toward the copper hull, revealing twisted beams and plates that hinted at centuries of saltwater assault. The wreck's outline emerged slowly, a skeletal form lying tilted against the seafloor. Broken masts, partially buried in silt, cast long, wavering shadows across the sandy bottom. Small sediment slides revealed layers beneath the wreck, suggesting slow but persistent oceanic reshaping over decades. Even through the ROV's lenses, the scale of the site impressed the crew, each panel of corroded metal a testament to the relentless passage of time and the pressures of the deep. Panels of oxidized copper reflected in the ROV's camera, the corroded edges forming jagged lines that contradicted the ship's known schematics, leaving observers puzzled. Hull plating peeled in places, exposing ribs of structural support twisted at unnatural angles. Where copper had flaked, marine growth had taken root. Tube worms, anemones, and thick layers of biofilm covering surfaces like a silent reclamation. Some areas suggested human intervention, as if parts had been removed or damaged deliberately before the wreck descended to its final resting place. The combination of natural corrosion and unexplained alterations suggested a story both historical and mysterious, one that the crew struggled to decipher. Currents swept through the wreckage, stirring clouds of fine silt that obscured the lower decks, while brittle stars and amphipods clung to surfaces as if marking the passage of time. Periodic shifts in the water column revealed hidden corners of the vessel, long shadowed in previous passes. Tiny fish skirted the edges of collapsed decks, their movement triggering ripples in sediment that revealed unexpected hollows and depressions. The interplay of biological activity, sediment transport, and subtle water movement created a dynamic environment where each observation was ephemeral and each anomaly could vanish as quickly as it appeared. Among the wreckage, an odd cluster of objects appeared unnaturally intact, their shapes defying expectations for debris exposed to decades beneath crushing pressure. Cylindrical containers, their surfaces free of biofilm and corrosion, suggested either an unusually resilient material or interference after the wreck's descent. The ROV's manipulator arm hovered cautiously near these forms, revealing markings that hinted at careful construction rather than incidental loss. The placement of these objects, separated from the main hull and yet clearly associated with it, raised questions about cargo handling, intentional concealment, or post-sinking disturbance. Crew members debated whether the anomalies were products of oceanic forces, historical salvage attempts, or the subtle hand of some process still unknown to science. Archival records noted only the general route of the ship with vague references to storms and possible misnavigation, offering little clarity. Some suggested minor underwater landslides or slope failures could account for displaced cargo, while others proposed undocumented salvage activity, either during the vessel's operational life or in the decades after its sinking. Every hypothesis confronted gaps in historical evidence, underscoring how little was truly known about the final journey of the ship. Electrical systems on the ROV flickered as it maneuvered around entangled frames, cables and sediment flows, highlighting how even advanced technology struggled against the environment. Propeller wash from minor maneuvers stirred suspended particles, reducing visibility to mere meters, while sudden eddies threatened to push the vehicle into protruding beams. Each new sweep required meticulous attention, careful adjustment of ballast and thrusters, and constant monitoring of sensors to avoid collision with both wreckage and seabed. The ocean, in this remote corridor, remained indifferent to human effort, revealing its secrets only with patience and repeated observation. According to archival shipping records, the vessel should have followed another course, leaving its present location puzzling and unexplained. Trade routes, storm warnings, and official reports placed the ship along a more northerly course, yet sonar and ROV data confirmed the wreck's location far to the south. The discrepancy suggested navigational error, a desperate maneuver to avoid storms, or even intentional deviation for reasons lost to history. Regardless, the mismatch between expectation and observation deepened the sense of mystery surrounding the site, hinting at choices and events that were invisible yet crucial to the ship's fate. Catalogued fragments and recovered artifacts offered only partial insight, as the wreck withheld the greater tale it held. Every recovered fragment, every scanned image, offered clues without forming a complete narrative. Questions about cargo, ownership, final route, and the forces that led to its sinking remained unanswered, leaving the team to reconcile the tangible evidence with the silent testimony of centuries beneath the ocean. The copper hull lies in quiet darkness, preserving secrets that the ocean refuses to reveal, each detail a riddle locked in corrosion and shadow. The capsule beneath the Labrador trough. The research team had assembled above the Labrador trough under a pale, overcast sky, preparing to retrieve a capsule that had rested undisturbed for months beneath the icy currents. The vessel drifted slowly on the choppy North Atlantic waters, its sonar and telemetry systems running constant diagnostics, while scientists and technicians monitored the descent plan. The capsule, part of a long-term oceanographic study, had been deployed to record sub-seafloor temperature gradients, current velocity, and microseismic activity in the deep trough separating Newfoundland and Greenland. It had functioned without interruption until a recent data anomaly prompted the urgent recovery. What had been planned as a routine lift now carried the weight of uncertainty, as the Labrador trough was notorious for its unpredictable and violent undercurrents, and the abyss beneath held shadows that instruments could not fully interpret. Hundreds of kilometers long, the trough beneath the surface stretched, its steep walls cloaked in darkness, where temperatures hovered barely above freezing and the water pressed against every hull and sensor with crushing intensity. The seabed at these depths was largely silty, formed from glacial melt deposits and the slow accumulation of organic detritus, and the topography was scarred by faults, ridges and narrow canyons carved over millennia. The capsule itself had been engineered to withstand these conditions: a reinforced titanium shell, thrusters for minor positional adjustments, and a network of acoustic modems to relay data back to the surface. Yet, despite its design, the harsh environment posed challenges beyond structural integrity. Electromagnetic interference, biofouling, and the sheer weight of the water column made any operation precarious. The crew's task was to navigate this labyrinth of pressures and darkness, bringing the capsule safely back without disrupting the fragile instruments inside. As the capsule began its slow ascent, sonar feeds revealed the expected sediment patterns, yet subtle shadows and irregular contours hinted at something the charts did not account for. Initially, the anomalies were dismissed as minor eddies or sensor noise. The Labrador trough was known for unexpected bottom currents that could shift sediment drifts unpredictably. But as the lift progressed, the irregularities became more pronounced, with echoes suggesting depressions and hollows larger than any natural formation nearby. The ROV accompanying the lift transmitted images that appeared normal at first glance, yet scrutiny revealed patches of seabed that seemed to vanish into darkness, areas where no sediment, rock, or known geological feature could explain the readings. The team on deck exchanged uneasy glances, recognizing that the situation demanded heightened vigilance. Then, without warning, the ocean floor beneath the capsule appeared to vanish, revealing a hollow that descended into blackness deeper than any nearby mapped trench. The sonar returns displayed a vast void, its walls irregular and shadowed, creating an almost vertical descent that the lift system could not accommodate. The tether lines of the capsule fluctuated in tension, as if the weight below had shifted abruptly. Attempts to reposition the ROV closer for visual confirmation revealed nothing. Its floodlights illuminated only the edges of sedimentary cliffs, leaving the central abyss in total darkness. Oceanographers aboard speculated on glacially scoured cavities or collapsed subsea floor chambers, but none had been mapped, and no natural explanation fully accounted for the size and geometry of the hollow. The capsule hung above it, seemingly suspended between mapped reality and an unknown chasm that had formed without warning. Efforts to stabilize the lift were met with inconsistent cable tension, sensors fluctuating wildly as if the very currents had taken on a mind of their own. Hydraulic pumps on the winch strained under the unpredictable load, and instruments aboard the capsule reported minor orientation shifts despite its thrusters operating at maximum compensation. The acoustic modems, normally precise, began emitting distorted signals, garbled echoes that made telemetry uncertain. Crew logs noted a growing sense of disorientation on the bridge. The horizon of the water, the readings from instruments, and the visual cues from cameras all seemed at odds with each other. Even experienced technicians who had worked in deep ocean recoveries for decades felt a subtle but unmistakable unease, a suspicion that the capsule was hovering over something the charts and science could not fully describe. The ROV lights caught glimpses of shapes that seemed to move against the current, and sonar returns traced lines that vanished as soon as they were detected, leaving only the silence of the abyss. Particles of sediment rose from the void, swirling as if disturbed by an unseen hand, and faint acoustic pulses were recorded, rhythmic and irregular, that did not correspond to any machinery or natural phenomenon known in the region. Efforts to lower additional supports to anchor the capsule were hampered by erratic currents that seemed to flow upward from the hollow itself, carrying fine silt that reduced visibility to near zero. Each new attempt revealed further anomalies, from angular shadows to temperature fluctuations that could not be explained by known hydrothermal activity. The abyss appeared to resist observation, defying instruments and human perception alike. After hours of indecipherable readings and repeated equipment strain, the operation was abandoned, the capsule left dangling just above the yawning void as the crew retreated to uncertain safety. Surface reports logged the retrieval attempt as incomplete, noting unexpected environmental stress on both the vessel and instrumentation. The hollow beneath the capsule remained unmeasured, its true depth and dimensions unknown. Acoustic monitors continued to detect faint, intermittent signals from below, and attempts to return at a later date were postponed indefinitely due to safety concerns and the unexplainable nature of the void. For the scientists and crew, the Labrador trough had revealed a section of the deep ocean that challenged the limits of technology and understanding, a place where even routine recovery operations became encounters with the unknown. A presence lingered in the abyss beneath the capsule, unseen yet unmistakably present, as if the ocean itself were guarding its secret. The drowned observatory of the Seyells basin. A series of sharp, rhythmic taps echoed through the ROV's hydrophones as it hovered above the collapsed observatory, drawing the crew's attention before any visual confirmation could be made. The waters of the Seyells basin were calm on the surface, yet the pressure nearly 3 kilometers below compressed every module, sensor and cable into a brittle stillness that amplified the slightest sound. The observatory, deployed years earlier to monitor ocean currents, thermal gradients, and deep-sea seismic activity, had not been recovered due to persistent equipment failures. Now, suspended above its twisted remnants, the crew and their machines were confronted by a signal that made no sense. A tapping pattern both deliberate and erratic, echoing through corridors crushed by the weight of water. The hydrophones, designed to detect minute tremors in the abyss, recorded the pulses with an intensity that made every technician lean forward, straining to interpret something that no one had ever encountered in previous deep-sea recoveries. Lights from the submersible swept across twisted steel frames and scattered instrumentation, revealing sediment patterns that shifted against the current in ways that no natural flow should allow. Fine silts, normally inert at these depths, rose in miniature clouds, tracing currents that bent unpredictably around collapsed modules. The observatory's exterior panels had been warped inward, exposing compartments that once housed microprocessors, hard drives and acoustic arrays meant to relay continuous data to the surface. In some sections, pressure-resistant doors hung ajar, suggesting internal movement despite the abyssal pressure that should have immobilized everything. The shadows cast by the ROV's lights created an illusion of motion, but subtle disturbances in the sediment and minor vibrations in the water suggested something more tangible, something interacting with the observatory from within its collapsed interior. Embedded sensors and data cores within the observatory had once recorded months of oceanographic conditions, temperature gradients, current velocities, and seismic tremors, but now lay buried or exposed, vulnerable to the abyssal pressures surrounding them. The acoustic arrays, designed to detect microseismic shifts and biological activity across the basin floor, had transmitted coherent data for months, offering insight into tectonic microfaults and migratory patterns of deep-sea fauna. Those same sensors now picked up signals that could not be correlated with any known natural process. Subtle vibrations, almost imperceptible shifts in the modules, and repeated tapping that bore a cadence not associated with machinery or environmental stress. Logs from prior expeditions highlighted the predictability of the basin's currents, but the present readings defied all expectations, registering activity that seemed both localized and impossible to trace definitively. Manipulator arms jerked unexpectedly, and camera feeds flickered as if the structure itself responded to the presence of the crew, each sound amplified by the water's density into a haunting resonance. Attempts to retrieve hard drives or attach stabilizing lines were met with variable resistance, as though the instruments themselves opposed the intervention. Minor currents funneled through collapsed corridors at angles inconsistent with the broader flow of the basin, carrying suspended sediment in patterns that occasionally obscured the ROV's cameras. Crew members monitoring the live feeds felt a creeping unease. Spatial cues from the cameras suggested corridors extending farther than schematics indicated, and angles shifted subtly in ways no human-made structure should allow. Every adjustment of the ROV produced a feedback loop, the tapping synchronizing or altering slightly in response, heightening the sense that the observatory itself was aware of their presence. Shadows moved where no object should exist, while hydrophones picked up subtle pulses that neither tide nor machine could produce, layering uncertainty onto every observation. The ROV's lights occasionally revealed glimpses of irregular shapes, twisted metal rods bending slightly, small clouds of disturbed sediment rising abruptly, and streaks of darkness within interior chambers. Acoustic analysis showed bursts of energy at irregular intervals, frequencies not consistent with any known oceanographic event or marine organism in the region. Sensors designed to measure pressure, salinity, and temperature fluctuations also produced readings inconsistent with expectations, showing localized microcurrents and minute unexplained eddies. The confluence of sound, motion, and shifting sediment created a sensory puzzle that refused to resolve, leaving the team with a mounting sense of disorientation and caution. Probing the interior with tethered cameras and flexible manipulator arms yielded sporadic results. Devices were caught on bent panels, signals glitched unexpectedly, and footage displayed fleeting frames where interior corridors appeared distorted. Even repeated passes failed to capture a complete map of the observatory's interior. Corridors seemed to lengthen, bend, or vanish under the pressure and the shadows. Crew members reviewed prior data from deployment, noting that the structure had withstood abyssal conditions for years without incident, yet now every module responded unpredictably. They hypothesized structural collapse or shifting sediment might explain minor anomalies, but the consistent rhythmic tapping suggested something more deliberate, an anomaly rooted not only in the environment, but potentially in something within the structure itself. After repeated failed attempts to retrieve the hard drives, the decision was made to retreat, leaving the observatory partially buried and the unexplained tapping continuing in the dark corridors below. Surface logs recorded subtle, ongoing acoustic feedback even after the ROV had ascended, while pressure readings showed transient fluctuations that could not be reconciled with natural currents. Subsequent attempts to return were postponed, leaving the basin with its silent, enigmatic occupant. Scientists reviewing the expedition noted the basin's resistance to observation, a reminder that Even with modern submersibles and high-fidelity instrumentation, some corners of the deep ocean remain beyond human comprehension, and that the drowned observatory might hold secrets never to be recovered or explained. Inside the drowned structure, a presence persisted, listening to every movement and responding in patterns that no human mind could anticipate. The lost sonar drone of the Mariana Ark. An irregular echo appeared on the vessel's sonar monitors, a precise silhouette that mirrored the very drone sent to chart the Mariana Ark's volcanic ridges. Scientists aboard the surface vessel leaned over the displays, scrutinizing the readings as the anomaly followed the drone's last transmitted course with eerie precision, despite no signal confirming its presence. The drone, a state-of-the-art autonomous unit with multi-beam arrays and side-scan sonar capable of resolving features under 6,000 meters of water, had been tasked with mapping abyssal ridges and nearby hydrothermal vents, recording both bathymetric data and seismic activity. Temperatures barely rose above 1 degree Celsius, and pressures exceeded 600 atmospheres, conditions that would crush any inadequately designed submersible. Yet here, in this extreme environment, appeared a sonar return that mirrored the drone's dimensions exactly, moving as if it anticipated every command sent from the surface. Crew members whispered to each other, noting that the anomaly's precision defied natural explanation and seemed almost deliberate, a ghostly echo inhabiting the trench alongside the machine it replicated. At the bottom of the crushing deep, the Mariana Ark's terrain spread in a network of sharp ridges and abyssal slopes, interspersed with vent chimneys that released mineral-rich, near-boiling water into the near-freezing surroundings. Basalt outcrops jutted sharply from the trench floor, fractured by tectonic motion and overlaid by fine volcanic ash and sediment transported by complex thermohaline currents. These currents twisted unpredictably around fissures and vent plumes, creating localized eddies that could distort acoustic readings, while the drone's sonar arrays accounted for sound speed variations caused by cold, high-pressure water and minor thermal layering. Yet the echo persisted with unerring fidelity, moving as if it had intimate knowledge of the environment and the drone's path. Even subtle disturbances, such as sediment clouds rising from vent-induced turbulence or microseismic tremors beneath the crust, failed to alter its trajectory. Scientists logged these readings meticulously, realizing that the anomaly seemed to exist both within and apart from the known rules of physics, a pattern of acoustic perfection that no software or mapping protocol could replicate. Triangulating the anomaly against prior mapping surveys produced only contradictions. Each calculation suggested a physical object in the water column, yet repeated ROV passes revealed nothing but mineral-laden currents, fractured basalt and vent plumes. The anomaly's behavior did not correspond to any natural reflection, current-driven sediment displacement, or acoustic interference, nor did it match any previously recorded subsea objects in the Mariana Ark's database. Analysts compared sonar signatures with known marine fauna, microseismic events, and volcanic vent outputs, but every check failed. The ghostly shape not only followed the drone's path, but occasionally accelerated or slowed in perfect coordination, as if tracking and anticipating the drone's actions. Crew members began documenting every ping and echo with painstaking precision, noting the timing of each pulse and the harmonic irregularities in the sonar return. Even the most experienced engineers admitted that they had never encountered a phenomenon that so precisely mirrored human technology while remaining untouchable and invisible to every visual or physical sensor. Following the drone's last recorded path, ROVs were deployed, their lights cutting through the opaque, mineral-rich waters that swirled around vent chimneys and basalt spires. The submersibles carried secondary sonar arrays, high-resolution cameras and manipulator arms, all calibrated to detect any object capable of producing the duplicate sonar signature. As the ROVs descended into narrow trenches and steep ridges, currents buffeted the submersibles unpredictably, carrying suspended sediment in clouds that obscured the seafloor and occasionally interfered with sonar readings. Despite repeated passes through every predicted location, no drone or other physical object was located. The anomaly persisted, moving with a precision that suggested awareness, as if it could respond to the ROV's movements and maintain a mirrored trajectory. Crew members took turns monitoring instruments, noting every unexpected deviation or fluctuation, their unease mounting with each new observation of this unexplainable echo. Sonar readings continued to confound the team, capturing subtle energy spikes and faint harmonic pulses that did not correspond to any known natural or technological source. Magnetic sensors recorded transient fluctuations near the anomaly, though no metallic object could be located. Even when the ROVs adjusted scanning frequencies and angles, the echo responded in ways that defied prediction. Small bursts of turbulence, caused by vent plumes or minor tremors, could have shifted the signal slightly, but instead it remained perfectly consistent, replicating the drone's exact outline and movement in real time. Analysts began cross-referencing historical expedition logs, searching for similar patterns in previous sonar surveys of the Ark, but found none. Each dataset reinforced the unsettling conclusion: the anomaly was deliberate, adaptive, and intelligent in a manner that no marine engineer or oceanographer could explain. The crew adjusted their instruments repeatedly, testing different search strategies, yet every maneuver only reinforced the anomaly's persistence. The ghostly echo anticipated changes in course, seemed to maintain a fixed distance from the ROVs, and at times even appeared slightly higher in the water column than the drone itself. Video footage showed only shadows and faint sediment plumes stirred by the ROVs, while sonar arrays confirmed the precise duplication of the drone's dimensions. Efforts to triangulate, remap, or even physically approach the signature failed. Scientists aboard noted in their logs the strange correspondence between the anomaly's timing and the drone's path, acknowledging that no known acoustic, geological, or biological mechanism could account for such behaviour. With no wreckage recovered and the drone's signature persisting in the sonar logs, the mission was reluctantly called off. Even after the ROVs surfaced, surface instruments continued to detect faint echoes and minor energy anomalies, suggesting that the phenomenon persisted long after human observation ceased. Analysts reviewed every chart, every pulse, every minor spike, and yet the anomaly resisted explanation. The Mariana Arc, with its tectonic volatility and hydrothermal complexity, had revealed a mystery that neither advanced technology nor scientific expertise could fully resolve. The drone's disappearance, coupled with the persistent, ghostly echo, left a record that would challenge every subsequent mission to the trench. Where sunlight never reaches in the depths, something unseen had learned to imitate human technology, leaving traces that no one could fully decipher. The pressure cage of the Chatham Abyssal Plain. The vessel's cranes groaned as they readied the reinforced pressure cage for its descent into the Chatham Abyssal Plain. The crew, aware that every cable, bolt and winch would be tested against forces hundreds of times stronger than those at the surface. The cage had been designed to carry seismic instruments and environmental sensors to the seafloor, an array of delicate but essential technology encased in steel, capable of resisting pressures exceeding 600 atmospheres. Deckhands checked lines and pulleys, engineers monitored gauges, and scientists reviewed data logs from previous deployments, all acutely aware that the abyssal environment would offer no mercy for human error. Even minor miscalculations in weight distribution, cable tension, or descent speed could have catastrophic consequences at such depths. The operation was meant to be routine, yet the crew felt a persistent tension, a quiet unease that seemed to grow as the cage loomed above the open water, ready to enter a world no human could ever see firsthand. Steel plates thick enough to resist 600 atmospheres were cold and slick with condensation, reflecting faint light from deck lamps as the abyss below rippled with unseen currents and drifting sediment clouds. The cage's framework had been tested extensively in pressure chambers, but simulations could never fully replicate the Chatham Abyssal Plain, an area defined by deep trenches, sediment-covered plains, and unpredictable currents. Thermaline flows, though slow, carried mineral particles and microscopic detritus across the seabed, sometimes creating sudden, localized turbulence that could strike an unprepared instrument or cable. Engineers double-checked the buoyancy modules, ensuring the cage's ballast was precisely calculated, while the crew adjusted winch tension to compensate for any unexpected drag. Even the faintest ripple could cause a cascade of vibrations along the suspension lines, and every detail mattered in a place where human survival was impossible without mechanized intervention. Hands gripped controls and clipboards alike, eyes flicking between gauges and monitors as the crew anticipated the moment the cage would leave the surface, carrying instruments designed to survive a world humans could not enter. Scientists reviewed environmental profiles, confirming temperature near 1 degree Celsius and salinity within expected ranges, while deckhands exchanged terse instructions about descent speed and cable slack. The vessel pitched gently with the swell, a reminder of the ocean's omnipresent power, even above the abyss. Every member of the team was acutely aware that they were about to commit complex machinery to a vast alien environment, one that could crush steel and distort human calculations with pressure and turbulence. Yet the mission proceeded methodically, each movement deliberate, each adjustment weighed against potential catastrophe, the anticipation as much psychological as operational. The cage slipped beneath the waves, its frame vanishing into darkness while sensors relayed sparse readings, currents tugging unpredictably, and sediment plumes swirling around the descent like ghosts of long-forgotten debris. Lights on the submersible support vehicles cast faint cones through the near-black water, revealing nothing beyond clouds of suspended particles and the occasional reflection of basaltic outcrops. Pressure sensors relayed incremental data to the bridge, confirming that the cage's hull remained intact and descent velocity matched calculated parameters. Yet the sheer emptiness surrounding the cage amplified a sense of isolation, as if the machinery and crew were suspended in a world entirely divorced from human experience. Observers noted subtle oscillations in the suspension lines, initially attributed to currents, but the timing did not align with the recorded flow patterns, and a faint but persistent vibration threaded through the winch system. A subtle jolt passed through the winch lines, barely enough to register, yet the crew instinctively leaned forward, noting the cage's frame shudder in ways that no current or cable tension could explain. Instruments recorded the event as a slight acceleration, but the magnitude was inconsistent with environmental conditions or the cage's ballast. Engineers recalibrated load sensors and cross-checked cable strain, yet the anomaly repeated moments later, slightly stronger, as if something within the cage had shifted. The crew murmured theories, ranging from trapped pockets of sediment to unexpected interaction with microfauna, but none could fully account for the precise directional strikes transmitted through the suspension lines. Each subtle tremor added to the tension, an invisible presence asserting itself within a world of steel, water, and pressure. Repeated strikes rattled the sensors and vibrated through the hull, irregular in timing but unmistakably coming from within the cage, prompting hurried notations and murmured speculation about forces unseen beneath the abyssal expanse. The cage's reinforced frame emitted low groans as the vibrations propagated through its steel lattice, registering on both acoustic and mechanical sensors. Even the small submersible deployed to observe the descent reported indistinct shadows and disturbed sediment around the cage, though no object or organism could be discerned. The strikes had a rhythm, though inconsistent, as if some intelligent or mechanical entity within the cage were testing its environment. Crew members compared readings against historical data from prior deployments, finding no precedent for any natural or mechanical cause, further heightening the sense that something beyond understanding had intervened. A small submersible was dispatched to inspect the cage, its lights cutting feeble arcs through the black water, yet every attempt to observe the source of the strikes ended in swirling sediment and a frame that shivered as if alive. The ROV's cameras captured images of the abyssal plain, where soft sediments and sparse benthic organisms were disturbed by the cage's presence, but nothing appeared capable of producing the repeated shocks. Thrusters and manipulator arms failed to provoke or interact with any visible object, and sonar imaging showed only the cage itself, rocking slightly without external influence. The persistent, unseen disturbance left the crew disoriented and anxious. Instruments suggested something interacted with the cage, but every visual confirmation failed. After hours of mounting tension, the decision was made to halt the lift. The cage remained submerged, the instruments intact, but the mystery unresolved, leaving the crew with nothing but data logs and a lingering unease. The winch slowly retracted the line without attempting to lift the cage, and surface readings continued to show faint vibrations and intermittent anomalies. No further explanation could be determined from the sensors, and the area around the cage was logged meticulously for future reference. The Chatham Abyssal Plain, already one of the most remote and geologically stable regions of the ocean floor, had preserved an enigma that challenged both engineering and scientific understanding. In the crushing silence of the Chatham abyssal plain, something moved within human steel with intent, leaving questions that no oceanographer or engineer could ever answer. The quiet hull of the Beaufort Crescent. Ice scratched against the hull of the surface vessel as the crew prepared to descend toward the overturned Beaufort Crescent, aware that beneath the frigid waves lay a steel ghost that had not been touched for decades. The mission was straightforward on paper: locate and survey the sunken vessel, recover any instruments or cargo still intact, and document the wreck for archival and safety purposes. Yet the Arctic waters of the Beaufort Sea, with temperatures hovering just below freezing and currents that shifted unpredictably, had a way of complicating even the simplest operations. The crew meticulously inspected winches, submersibles and tether lines, each aware that once the descent began, human control would be limited and that the ocean could conceal dangers both natural and inexplicable. Overhead, the sky was a pale, featureless grey, reflecting the stark isolation of the region and echoing the silence that awaited them below. The submerged vessel rested at an angle of nearly 30 degrees, its darkened deck hidden beneath a layer of sediment, while currents carried shards of ice and silty water across the abyssal plain. Long exposed to pressure, cold in the subtle movement of the seabed, the Beaufort Crescent had become a muted, ghostly presence on the seafloor. Its steel hull, originally designed to withstand ice pressure at the surface, had contorted over decades, rivets stretching and warping under uneven sediment loads. Debris from the ship's superstructure, twisted ladders, broken railings and scattered cargo containers lay partly buried, creating obstacles for approaching submersibles. Even small shifts in current caused the hull to sway minutely, a reminder of the latent tension embedded in every ton of steel and ballast. Lights from the submersible swept across the hull's riveted plates, revealing twisted ladders, warped cabins, and the occasional glint of brass fixtures, yet the silence beneath the water was so profound that even the faintest vibration seemed amplified. Crew members leaned forward over monitors, listening for subtle echoes that might betray the presence of loose objects or hidden structural weaknesses. Cameras recorded every angle, yet the dim, filtered light revealed little beyond shadow geometry and shifting sediment. Even the hum of the submersible's thrusters seemed muted in the dense, cold water, and small plumes of displaced particles lingered like ghostly curtains. The environment created an uncanny tension, making it difficult to distinguish between natural movement and something that felt deliberate. A tremor traced through the hull, small enough to be mistaken for a current or cable shift, but the crew noticed it coincided exactly with the movement of the submersible above, as if the ship itself were responding to their presence. Monitors displayed tiny oscillations that did not match any environmental modelling, and sensors indicated micro-vibrations propagating along the steel plates. At first, engineers suggested equipment interference, but repeated observations confirmed that the tremors occurred only when human activity, thruster adjustments, manipulator arm movement, interacted with the hull. The timing was too precise, too deliberate to be random, leaving the crew uneasy with the sense that the ship was more than a passive object in the abyss. Reflected shadows in the portholes shifted in near-perfect timing with the ROV's thrusters, and instruments recorded micro-vibrations that mirrored every movement of the crew, an uncanny imitation that could not be explained by physics alone. The lights caught on warped metal and residual cargo, producing fleeting reflections that seemed to anticipate the submersible's movements. Even subtle manipulations, like adjusting the camera arm, coincided with imperceptible creaks in the hull, registering on strain sensors. The psychological weight of watching a vessel appear to respond without engines or crew settled heavily over the team, blending scientific curiosity with a growing unease. Every creak, shadow and ripple seemed amplified in the oppressive silence of the Arctic waters. Upon brushing the deck, the submersible's manipulator caused sediment clouds to rise, yet the vibrations persisted even when no physical contact occurred, while drifting ice and shifting currents created a world of deceptive reflections and distorted perception. The crew attempted to differentiate between natural environmental effects and the inexplicable signals recorded by strain gauges, but every anomaly resisted explanation. Tiny amphipods and benthic organisms occasionally scuttled past the lights, yet their movements could not account for the precise mirroring of human actions. The combination of frozen currents, low temperatures, and muted acoustics created a surreal environment where human perception was challenged and the line between mechanical reality and psychological interpretation blurred. Using sonar pings and gentle tugs to probe the ship failed to provoke a response beyond the subtle, mirrored tremors, leaving the crew frustrated and uneasy as the hull maintained an eerie, silent autonomy. Sonar scans revealed only the geometry of the vessel and its immediate surroundings. There was no hidden machinery, no trapped animals, and no physical explanation for the vibrations that matched the submersible's every movement. Each adjustment of the manipulator arm, each repositioning of the ROV produced a mirrored effect that sensors could capture but cameras could not confirm. Despite their expertise, the team confronted a phenomenon that challenged the limits of observation and understanding, an interaction between human presence and a submerged object that seemed both impossible and immediate. Having inspected carefully for hours, the decision was made to ascend, leaving the Beaufort Crescent in its dark, frozen resting place, with data recorded but the source of the responsive vibrations unresolved. Tether lines were slowly reeled in, cameras capturing final angles of the ship as it sank deeper into shadow. Ice sheets drifted overhead, casting dim, shifting patterns into the water, while the vessel below remained eerily still yet perceptibly aware, every creak and tremor logged but unexplained. The crew reviewed notes and sensor data, cataloguing every irregularity, yet no conclusion could be reached. The Arctic silence reclaimed the wreck, preserving both the mystery and the unnerving sense of observation. Under the Arctic silence, the ship remained, listening and reflecting, a vessel that moved without engines and waited without eyes. The sunken relay of the Ligurian drop-off. The Mediterranean wind slammed against the bridge as the crew prepared to lower the submersible toward the Ligurian drop-off, a remote stretch of steep underwater slopes where a vital communications relay had gone silent. This relay formed part of a deep-sea monitoring network, designed to transmit seismic and oceanographic data across the western Mediterranean, yet its failure threatened the continuity of months of sensitive research. Waves rolled under a grey, turbulent sky, tossing ice-cold spray against the vessel as technicians confirmed that every cable, thruster and acoustic modem was fully operational. The urgency of the mission was palpable. Each delay risked losing critical data, while the Ligurian drop-off, with its uneven slopes and strong currents, offered no margin for error. Crew members spoke sparingly, their attention divided between monitoring instruments and preparing the submersible for a descent into the shadow depths below. Technicians double-checked every tether thruster and acoustic modem, aware that even a minor misalignment could render the deep-sea mission futile beneath crushing pressures exceeding 300 atmospheres. The submersible itself was a compact, reinforced vehicle, equipped with cameras, manipulator arms, and sensor arrays capable of relaying information in real time to the surface. Engineers reviewed data from previous deployments, noting how the steep gradients of the drop-off had challenged earlier missions, with unpredictable currents and sediment slides. Acoustic signals were recalibrated and emergency protocols rehearsed as the team balanced operational precision against the ever-present risk of environmental hazards. Even a slight miscalculation could strand the submersible or damage the relay beyond repair, and everyone aboard felt the weight of responsibility as the descent approached. The submersible slipped into the green-black water, currents twisting around the rocky seabed, and sensors recorded sharp temperature gradients and sediment plumes that painted an uneven canvas across the abyssal slope. Light from the vehicle's lamps penetrated only a few meters before being swallowed by darkness, revealing jagged outcrops and scattered debris that seemed almost suspended in the water. Small eddies swirled against the submersible's hull, shifting silty clouds that obscured vision and complicated maneuvering. Pressure gauges climbed steadily as the vehicle descended, the metal hull creaking faintly under the weight of 300 atmospheres, a constant reminder of the ocean's indifference. Even with advanced guidance systems, every movement required careful calculation, as the drop-off offered hidden dangers in the form of sudden overhangs, sharp rocks, and unpredictable sediment flows. A sudden fluctuation in the relay's acoustic signal startled the crew, the intermittent pulses forming a pattern that seemed deliberate yet defied known marine or mechanical behaviour. Initially, technicians assumed interference from local currents or reflections from the rocky seabed, but the signal's precision and timing suggested something far more unusual. Monitors displayed brief surges of energy from the relay, followed by moments of complete silence, and the pattern repeated with unnerving regularity. Crew members leaned closer to screens, noting how the anomalies aligned with the submersible's position, as though the relay were aware of its presence. The deeper the vehicle went, the more pronounced the effect became, sending a ripple of tension through the team. Instruments detected subtle interference with the submersible's guidance system, a rhythmic distortion synchronized with the relay's pings, forcing the team to question whether the anomaly was electrical, mechanical, or something altogether stranger. Thruster adjustments produced delayed responses, manipulator arms wavered unexpectedly, and acoustic feedback loops interfered with the onboard navigation software. Attempts to recalibrate sensors temporarily stabilized readings, but the pattern reasserted itself with each corrective measure, as if the relay were actively resisting observation. Engineers cross-checked signal logs against historical environmental data, finding no precedent for the disturbances, and even considered whether deep-sea creatures might interact with electronics, yet the precision of the interference suggested otherwise. Hands moved over consoles with rapid precision, attempting to compensate for the shifting signals while the submersible hovered above jagged rock formations, yet every correction seemed to be anticipated by the relay itself. Crew members issued terse instructions to one another, balancing careful maneuvering with the need to remain within safe operating parameters. The submersible's manipulator arms probed the surrounding area, nudging rocks and sediment aside, yet the relay's responses continued in perfect alignment with every action. Each subtle adjustment of the vehicle caused a corresponding fluctuation in acoustic readings, reinforcing the sense that something beyond mere mechanics was at play. Anxiety mounted as the team realized that even the simplest retrieval procedures might be compromised by forces they could neither see nor predict. Cables rattled, and lights flickered as currents surged unexpectedly along the drop-off. But the most perplexing disturbances came from within the relay's own field, suggesting an intelligence or force beyond comprehension. Sonar pings returned faint, irregular echoes, distinct from the natural contours of the slope, while optical cameras captured nothing beyond sediment clouds and jagged rock faces. The submersible struggled against microcurrents and subtle turbulence, yet the relay appeared entirely unaffected, maintaining a presence that was both elusive and assertive. Crew members documented every anomaly with meticulous care, aware that no immediate explanation existed, and that the relay might remain an enigma long after their departure. With careful precision, the submersible ascended, carrying partial readings and detailed logs, leaving the relay suspended in the dark waters, its intermittent signals unanswered and enigmatic. Surface conditions had worsened, winds whipping across the deck and waves striking the vessel with renewed force, making any further descent inadvisable. Instruments were secured, tethers reeled in, and data transferred for analysis. Yet the anomaly persisted in the logs. The relay signals remained irregular, precise, and inexplicably responsive. Even after hours of review, the team could offer no definitive conclusion, leaving a deep sense of unease and unfinished inquiry. A relay persisted somewhere in the Ligurian depths, continuing to emit coded whispers that no human could interpret, as if the ocean itself had learned to speak in secret. The drift crate of the Solomon Passage. The crate had been spotted months earlier on deep-sea sonar, drifting silently along the steep contours of the Solomon Passage, and today a retrieval team was finally dispatched to investigate its peculiar trajectory. Located between the islands of New Georgia and Bougainville, the passage is notorious for its narrow, funneling currents and steep underwater slopes, conditions that can accelerate debris to unpredictable speeds. Researchers had initially dismissed the drifting object as ordinary cargo lost from passing vessels, yet repeated tracking revealed a path that defied typical current patterns. The mission combined scientific curiosity with operational necessity, not only to retrieve the crate, but to understand why it seemed to navigate the abyss with unnatural precision. Crew members prepared carefully, aware that in the depths of the Western Pacific, even the most routine operations could become perilous. Aware that strong, swirling flows could push the crate beyond reach in minutes, technicians secured the ROVs and calibrated thrusters, while oceanographers reviewed current patterns and sediment maps. The submersible team discussed navigation strategies, paying particular attention to localized eddies and gravity currents that might impede their approach. Sensors were checked for interference from suspended particulates, and acoustic modems were tested for reliable communication with the surface. Deep-sea retrieval required an unusual combination of patience and precision. The crew needed to remain responsive to every shift in the crate's movement, while accounting for natural oceanic variability that could disrupt even the most careful maneuvering. The submersible plunged into the inky depths, lights cutting through suspended sediment, and soon the crate appeared, a dark rectangular silhouette hovering just above the rocky slope, motionless yet unmistakably present. Its steel-reinforced edges were coated with a thin layer of manganese nodules and fine silt, evidence of long-term exposure to deep water conditions. Cameras captured the crate's angular profile, while manipulators remained ready to engage, poised above the ocean floor. The currents at this depth, though less intense than near the surface, shifted unpredictably along the channel's contours, and the team noted how even small changes in direction affected the crate's alignment. Initial sonar readings suggested no biological activity nearby, yet the object seemed almost alive in its stillness, a rigid presence defying the chaos of the surrounding waters. As manipulator arms approached, the crate shifted slightly against the prevailing current, a motion too precise to be random, and it continued to drift in a path that defied natural flow. The movement was subtle at first, a gentle slide sideways, yet each adjustment coincided with the team's positioning. Thrusters nudged the submersible closer, and the crate moved in a way that suggested anticipation, slipping just beyond the manipulator's reach. Oceanographers reviewed current profiles in real time, confirming that no natural force could produce the observed motion, and the crew exchanged uneasy glances as the crate continued along its mysterious path. Winches rattled and tethers tightened. ROVs maneuvered into position, but the crate responded with subtle adjustments, sliding aside as though aware of each approach and avoiding contact with calculated timing. Attempts to trap the crate with tethered nets were frustrated as it glided along ledges and shallow depressions, exploiting microcurrents to evade capture. Every action of the submersible produced a mirrored effect in the crate's trajectory, and the team began to question whether the object's movement was guided by some internal mechanism or by forces not yet understood. The combination of deep pressure, low visibility and unpredictable currents created a tense ballet between human control and the crate's enigmatic motion. Sensors recorded microcurrents and eddies that could not account for the crate's movement, and sonar imaging revealed it tracing loops and angles as if it possessed a hidden guidance, deliberately evading capture. Detailed motion logs showed acceleration patterns inconsistent with passive drift, and repeated attempts to calculate its velocity against current profiles yielded inexplicable results. The crate appeared to anticipate changes in the submersible's trajectory, maintaining a consistent separation while navigating narrow channels of rock and sediment. Crew members noted that even the slightest pause or misalignment from their side seemed to provoke a counter-adjustment in the object's motion, reinforcing the sense of intentionality behind its path. High-definition cameras captured every shift and tilt, while instruments logged the crate's minute accelerations, yet no mechanism or marine life could explain the controlled, repeated motions. Close-up images revealed pitting and corrosion consistent with long-term immersion, but nothing that could account for propulsion. Tiny crustaceans occasionally clung to its surfaces, moving with the currents rather than influencing the object's path. Data streamed to the surface, creating a record of baffling precision that defied both physics and expectation. Every observer felt the growing impression that the crate had become an autonomous entity, responding to the environment and the crew in equal measure. Reluctantly, the team ascended, leaving the crate suspended among the swirling currents, their logs full of data but their questions unanswered, haunted by the sense that the object had acted with purpose beyond human comprehension. The ascent required careful attention to tether strain and thruster output, as even minor miscalculations could damage instruments or the submersible itself. Once back aboard, the crew reviewed the recordings in silence, aware that the mystery remained unresolved. The crate's path, though fully documented, offered no explanation, its movements as deliberate and elusive as the abyssal environment that nurtured it. Drifting through the Solomon Passage, the crate moved with a silent intent that no map, sensor, or human hand could ever predict. The fault line wreck of the Andaman Verge. The Andaman Verge stretched like a jagged scar beneath the waves, and the deep sea recovery team descended to investigate a wreck precariously perched along its active fault line. Located in the northern reaches of the Andaman Sea, this steep, narrow trench forms part of a complex tectonic boundary where the Indian plate meets the Burma microplate. Historical seismic records show frequent microquakes, and underwater surveys have revealed a maze of fissures and scarps that make any recovery operation hazardous. The wreck itself, an unremarkable steel-hulled vessel from decades past, had become lodged atop fractured rock, its twisted bulk a silent reminder of the ocean's ability to claim what human engineering cannot fully secure. For the crew, the mission combined archaeological curiosity with operational urgency, aware that even a minor tremor could send the vessel tumbling into the abyss. Submersibles were checked and rechecked, their thrusters calibrated for rapid maneuvering, while geologists reviewed fault line surveys and seismic histories to anticipate any sudden movement of the seabed. Engineers confirmed that all manipulator arms and winches were operational, and acoustic communication systems were tested to ensure uninterrupted coordination. The team studied previous reports of sediment slippage and tectonic creep, noting how sections of the seabed could move unexpectedly even without a detectable quake. Risk assessments weighed heavily. A miscalculation could entangle cables, compromise the submersible, or damage the wreck beyond retrieval. Each member of the team knew that precision, patience, and constant vigilance were the only tools between them and disaster. The vessel's lights cut through the murky depths as the submersible glided past steep trench walls, revealing fissures that hinted at slow, relentless tectonic creep. Sediment clouds shifted and eddied in the narrow channels, occasionally obscuring cameras and sonar readings. Small rock outcrops cast long shadows across the wreck, creating an illusion of motion as currents nudged loose debris. The submersible's instruments registered minute tremors, subtle enough to be mistaken for mechanical vibration, yet patterns suggested the seafloor itself was slowly rearranging beneath them. Every foot of descent required careful monitoring, balancing the desire to reach the wreck with the need to avoid inducing instability in the surrounding fault zone. The wreck came into view, its hull fractured and tilted, wedged against slabs of rock that shifted with the faintest tremor beneath the vehicle. Corrosion had hollowed sections of the steel plating, and barnacles clung stubbornly to surfaces, making the vessel appear both fragile and immovable. Crevices in the surrounding rock hinted at previous slippage, and the team noted areas where sediment had cascaded into deep pockets along the trench. Cameras and sonar revealed that even gentle movements of the submersible sent fine particles tumbling along the slopes, a reminder that the wreck rested on an unforgiving, unstable foundation. A subtle jolt ran through the submersible as the seafloor shifted beneath the wreck, sediment cascading along fractures in a silent, eerie display of geological power. The movement was imperceptible at first, barely detectable through instrumentation, but enough to nudge the vessel and the surrounding rock. Crew members exchanged tense glances, their focus split between controlling the submersible and tracking the subtle tremors on the monitors. Each slight movement of the wreck altered the balance of cables and thrusters, turning a routine retrieval into a test of reflexes, judgment, and patience. Manipulators struggled to secure lifting cables as the wreck continued to tilt with imperceptible but inexorable movements, forcing the team to time every action with cautious precision. Even minor miscalculations risked entangling lines or causing further destabilization. The submersible maneuvered carefully along the fractured hull, noting areas of weakness and adjusting its approach for every tilt and sway. Sediment slides along the slopes reminded the crew that the wreck was never truly at rest, and that the fault line beneath it had the power to alter the operation at any moment. Every adjustment required microsecond calculations and a constant awareness of the environment, a delicate interplay between human control and geological unpredictability. Ascending carefully, the submersible recorded video and seismic data, capturing each small tremor and fracture as the wreck remained suspended between rock slabs and deep water currents. The team's logs would provide crucial information for understanding the dynamics of the site, even as the wreck itself remained only partially secured. Debriefing began immediately upon surfacing, with geologists highlighting subtle indicators of long-term fault-line activity that could explain sudden shifts. Although no dramatic collapse had occurred, the mission underscored the persistent risk inherent to underwater operations in tectonically active regions, and the crew carried with them an uneasy awareness of forces far beyond human control. Even with decades of oceanographic and geological study, the unpredictable shifts of the Andaman fault line left the crew with an uneasy awareness of forces beyond their control. Their instruments could measure tremors, map fissures, and record sediment behaviour, but nothing could predict the next imperceptible movement that might upend the wreck or jeopardise a future retrieval attempt. The ocean in this region remained a domain where human expectation met the limits of natural unpredictability, and even the most meticulously planned operation could only respond to the moment, never command it. The wreck persists along the Andaman verge, tilting and settling, a silent witness to the slow, inexorable movements that no human hand can halt. The forgotten vault of the Red Sea Rift. The Red Sea Rift yawned beneath the research vessel, a narrow, jagged valley where the deep-sea team descended to examine a vault that had eluded precise mapping for decades. Preliminary surveys had detected a dense metallic anomaly lodged within the rift's steep walls, an object that had resisted identification through sonar and remotely operated vehicles for years. At depths exceeding 2,000 metres, this section of the rift presented extreme conditions: near-freezing temperatures, crushing hydrostatic pressures, and occasional plumes of mineral-laden water from hydrothermal vents. The vault's origin was unknown, its shape vaguely hinted at by scattered readings and distorted reflections. For the expedition team, the mission represented a rare opportunity to study both an enigmatic artifact and one of the most geologically active portions of the Red Sea. Every step of the descent demanded precise coordination, for the combination of darkness, pressure, and complex terrain left little margin for error. Lights from the submersible barely penetrated the thick darkness, and the towering walls of the rift seemed to bend and shimmer as currents swirled around mineral-laden plumes. Tiny particles glimmered in the beam, catching light in unexpected angles that gave the illusion of movement, while the submersible's instruments registered subtle variations in temperature and salinity as it manoeuvred through narrow channels. Hydrothermal vents in the distance glowed faintly, their chemical emissions creating clouds of particulate matter that refracted the submersible's lights. Even before the vault was fully visible, the team sensed the disorienting effects of deep-sea optics. Distances appeared compressed or exaggerated, shadows stretched unnaturally, and the walls of the rift seemed to curve beyond the limits of their instruments. Every observation required careful calibration, and every maneuver risked misjudging depth or proximity. Glimpses of the vault appeared through suspended sediment, its edges distorted by refraction and shifting shadows, leaving the crew unsure of its true shape or distance. What had seemed a solid rectangular mass in sonar scans now appeared as a shifting form, sometimes elongated, sometimes compressed, as currents nudged clouds of mineral particles between the lights and the object. Video feeds revealed overlapping reflections and ghostly mirages, producing the unsettling impression that the vault was moving or dissolving before their eyes. The crew relied on triangulated readings from multiple sensors, yet even these offered only fragments of certainty. Each glimpse heightened a sense of unease. The object did not conform to the predictable geometry of human-made containers, nor did it resemble natural geological formations. Microcurrents diverted unexpectedly around the object, carrying fine particles in spirals, while sensors recorded subtle variations in temperature and salinity that had no obvious source. These disturbances were small but persistent, enough to cause instruments to fluctuate and thrusters to compensate continuously. The surrounding sediment occasionally lifted in delicate plumes, swirling as though the vault itself exerted an unseen influence on the water column. The team noted that even chemical readings from nearby hydrothermal vents did not account for the minor anomalies in localized salinity and density. It became apparent that the vault was not simply an inert object. Its presence, whether through mass, composition, or unknown electromagnetic properties, was affecting its immediate environment in ways that eluded conventional measurement. Crew members debated each maneuver cautiously, aware that their eyes and instruments could be deceived by the deep sea's unusual optical and chemical effects, as the vault seemed to evade every attempt at a precise approach. Attempts to attach lifting equipment were met with intermittent resistance, as minor shifts in the submersible's position, likely influenced by local microcurrents, created unpredictable angles. The decision-making process became a careful dance between observation, sensor data, and human intuition. Every adjustment revealed new ambiguities. Lights reflected off unseen ridges, shadows converged strangely, and sonar returns suggested outlines that vanished upon closer inspection. The team quickly recognized that this vault was a test not only of technology, but also of perception. Rising gradually, the submersible documented each anomaly and distortion, leaving the vault suspended in the gloom, untouchable yet recorded in layers of light, shadow, and sensor data. The camera feed captured refracted edges, glimmering plumes, and swirling particles that could be analyzed later. But the live experience remained incomprehensible. Each frame conveyed the strangeness of the object's presence, simultaneously monumental and evasive, silent yet imposing in its effect on the water around it. The crew logged environmental data with meticulous care, aware that the vault had imparted a subtle, indelible mark on the records of their instruments, leaving questions that would persist long after the dive ended. With all their instruments and expertise, the team confronted the limits of perception, realizing the vault's presence challenged both measurement and understanding in ways that no previous deep-sea operation had encountered. What could be known about the vault, its origin, its composition, its purpose, remained obscured by optical illusion, environmental distortion, and the natural limits of human observation. The Red Sea Rift had proven a formidable laboratory of unknowns, and the vault had emerged not merely as a physical obstacle, but as a reminder of the vastness of unexplored and unknowable domains beneath the waves. A vault endures in the shifting darkness of the Red Sea Rift, silently shaping the currents and shadows that dance around it, defying every attempt to know it fully.